Okay, I think we can get started. I see the number of our participants already going up, even though it's a different schedule for today. So thank you everyone for joining. And I want to say a special thank you to Misato Fukagawa, who's going to be the chair, Christoph Pant, and Akimasa Kataoka, because they're joining at very late times in their time zone. So thank you very much for joining us and for making the effort. And with that, I'm going to give the floor to Misato, who's going to chair the session today.
Okay, thank you very much. So good morning, good afternoon, good evening, everyone. So thank you for joining this day 3 for this HL 5 years conference. So today we're going to have the first half of session for the invited talks by Christoph and Akimasa. So let's get started. Christoph, please, start sharing your screen.
Thank you very much.
Okay, and also for participants, please, write your questions in Slido, and we will have the Q&A session for 15 minutes, about 15 minutes, and we can pick up the questions from Slido. So please, throw many questions. Okay, good.
I draw something. Sorry, I don't know.
Yes.
All right. Thank you, everybody. And I would like to thank in particular the organizer, because it's really a pleasure to be able to discuss kinematics at this meeting. And so far, I've really enjoyed the conference. I think you did a great job given the circumstances. And I think there's a really an added value having all these talks available for everybody. So today I would like to discuss the kinematic structures in planet-forming disks. And the motivation for that is that since the first image of HL2, we now have lots of images of disks with ALMA, and all of them, as soon as there's enough resolution, they show a lot of structure. We see gaps, rings, spirals, we see cavities, asymmetries. And of course, the key question is, what is the origin of all these structures, and can we connect them to planets? Which of them are connected to planet, and what can we learn from those structures on the process of planet formation? And today, in particular, I will try to discuss how the kinematics of this can help us to understand all these structures. So ALMA is a wonderful machine to observe the lines. It makes amazing images of continuum, but also in the various line. And this is because it has a really high spectral resolution. We can go down to 30 meters per second, which correspond to a resolving power of 10 to the 7. And on the left here, you have the first figure in the HL2 paper that was published in 2015. And the interesting thing is that this first figure was on the CO line. And you could already see that very interesting kinematics in HL2. So of course it was known, and Laura Perez explained it, that HL2 was an embedded source, that it has outflow, but we can already see some asymmetries and very interesting feature in the kinematics. So ALMA can reach super high resolution, both spatial and spectrally, but we cannot have both of them together. But we can get some very interesting compromises. For example, we can reach RMS of 5 Kelvin in brightest temperature, with a spatial resolution of 0.1 arc seconds and a high spectral resolution around 100 meters per second, and only in a few hours. And such an example of this kind of data set is the observation by Andrea Isela of HG163296. So on the left here, you have in red, you have the continuum disk where you recognize the rings that have been detected. And in blue, you have the 12 CO emission. And because ALMA has high spectral resolution, we can also compute moment maps. So the moment 1A on the right, which give us the integrated velocity along the line of sight for each pixel in the map. And of course, because of this high spectral resolution, the interesting thing is that we can scan in velocity through in frequency, which corresponds to velocity, through the disk. So on the right here, you have the same data as on the left, except instead of having the integrated map in velocity, I'm scanning in velocity across the different channels. And what we can detect, what we can see is that there's a very interesting butterfly pattern, which was predicted from Keplerian rotation. And I think one of the most amazing things is that we clearly see in this channel map the two CO surfaces. So we have one loop here that corresponds to the upper surface of the disk, and on the back, you have another loop that we see here that corresponds to the lower surface of the disk. So just to give you a better idea of what we're seeing, so here you have one of those channels, and those two emission bands here, this loop in the emission map correspond to the upper surface of the disk, and those two correspond to the lower surface. And in practice, what we're seeing is that the disk is inclined at roughly 45 degrees, and we have two CO surfaces because the CO is frozen in the midplane, so there's almost no emission. And because we have high spectral resolution in a given channel, we only see a narrow range of the disk, a small fraction of the disk where the projected velocity is equal to the setting in the interferometer. I found this amazing that ALMA was able to detect those two surfaces, and this is what has been predicted by, sorry, oops, can't change slide anymore. Yeah, sorry. That's what has been predicted by the model of chemical evolution in disk, even if CO is not really chemistry. One of the interesting things with CO is that because of the simple chemistry, we have a simple emission layer. So basically, if you look at a molecule like CO, you can divide your disk in 3 layers. So you have the upper surface here in red, which is atomic and ionized, which is photodissociated by the radiation from the star. In yellow here, you have the molecular layer, which is warm, and the midplane is cold, and all the molecules are going to be frozen on the dust grains. So the fact that we have these two narrow emission layers in yellow that can be probed by ALMA in the line is very interesting because it allows us to do the kinematics that I will present you in the next few slides. So there's a few things I would like to discuss today. The first thing is how we can use this CO map to map the thermal and velocity structure in the disks. Then I would like to discuss a little bit the constraints that have been obtained on the turbulence in the disk. I'll mention briefly the large scale flow that we can detect. And finally, I'll discuss the kinematics, and in particular, the non-Keplerian motion that we can see both in multiple systems, but I'll go very quickly because Nicolas Coelho is going to talk about that. And then the kinematics of planet-disk interaction. So I'll start by how we can use the molecular line, and in particular, the CO, to map the thermal and velocity structure in the disk. And I think it all started with science verification data on HG163296. So here on the left, you have the channel maps of the science verification data published by Itziar de Gregorio Monsalvo. And the first paper that looked at the kinematics on this data set was a paper by Katrin Rosenfeld. And what she realized very early on is that because we see those two structures, those two emission surfaces, the upper emission and the lower, we can basically map the emitting surface and fit a toll model, which is what she has done here. So in black and red, you have the two upper and lower emission surfaces that she's trying to match to each individual channel. So thanks to this data, she was able to reconstruct the emitting surface of the CO. And a bit later in the paper, she's already studying the effect of the vertical dependence on the velocity field and on the pressure gradient. And you can see here she has run some models where she's comparing the emission from a standard model where she had the vertical dependence, the pressure gradient, and we can see differences that we are now able to detect in the data. And if you want to know more about that source, in particular, Christian Rubb has a nice talk where he gives a nice detailed modeling of this emission. Another way, which is best a bit in what Katrin Rosenfeld did to reconstruct the emission surface, is to realize that if you have one channel map and you see an emitting surface here, if you rotate your emission map so that the semi-major axis of your disk is horizontal, if you take 2 points along a vertical line, they're going to be on the same orbit. So basically, you have an orbit here of the gas, which is an ellipse because your disk is inclined, and this orbit is going to be shifted from the star. So the center of the ellipse is going to be shifted just because of the altitude of the emitting layer. So there's a little bit of simple geometrical calculation to do, but if you measure those 2 points and if you do it along those emitting region in the disk, you can basically reconstruct the altitude and the radius at each point in the disk. And because we know the frequency of each channel map, you can also reconstruct the actual velocity inside the disk. And finally, because we use the 12CO line, which is an optically thick line, we can assume that the brightness temperature is almost equal to the excitation temperature. And because we are mostly observing low GCO line, we can also make the assumption that the excitation temperature is equal to the gas temperature. So using these channel maps, we can basically reconstruct the position, velocity, and temperature at any point in the disk. And that's what we've been trying to do this is the data on IM-Loopy. And you see the 12CO surface here in blue and the 13 and C18O. So as expected, we detect that the 13CO surface is lower than the 12CO. And an interesting thing is that a similar analysis can be done on scattered light images. So here you have an image of IM-Loopy by Henning-Havenos, where we see the flaring of the disk. And by fitting ellipses and by how much they are shifted as a function of radius compared to the star, Henning was able to reconstruct the scattering surface, the 2=1 surface in scattered light. And the interesting thing is that this surface is basically in between the 12 and the 13CO emitting layers. So that suggests that if we detect structure in the scattered light, somehow this should be potentially connected to some of the same structure in the channel maps. And I also refer you to a talk by Evan Rich, where he's trying to do basically the same thing, and also the talk by Antonio Garuffi, where he gives a nice overview of the sphere result. And as I was mentioning before, we can also reconstruct the velocity. So here you have the same curves where you have the velocity as a function of radius for the 3 isotopologues. So you have in blue the 12 and then 13 and C18O. And the first thing we noticed when we did that is that the 12CO is rotating slower than the 13CO, for example. And this is directly due to the dependence of the gravity at a higher altitude in the disk. So because the effective gravity is lower at the higher altitude, the 12CO is rotating a bit slower. And we fitted lines to the data points, and you see that the difference that we get between the two lines correspond exactly to what we see in the observation. So we basically exactly measuring this term in the velocity curves that we extract. And another interesting thing that we saw is that at large radius, here you see for example, the 12CO is below our model. And this is because of this term at large radius outside of 300 AU, that's where the gas density is dropping, because that's where we reach the taper edge in the density structure. And what we think we're detecting, it's because of this sharp drop in density, the pressure gradient is basically affecting the velocities that we measure. And interestingly, Tom Mowers was able to detect like winds. So another possibility is that this term is just part of non-Keplerian velocities that could be due to wind emission on top of the pressure gradient. And finally, another thing that we were able to do by separating those surfaces is that we can measure the brightness temperature. So here in 12CO, you see that as soon as we resolve the emission, the temperature is dropping with radius as expected. But in this, for 13CO in red there, we saw that the temperature is flat. So basically what we're measuring is that because the 13CO is optically thin, we're going down to the last molecular gaseous layer of CO just before the freeze-out region, and we can measure the vertical snow line of the CO. So we can basically map the temperature in the disk at different altitudes. So this is for all the points we have been obtaining using the 12 CO and all the points that have been obtained using 13 CO. And the background is a model that fits the observation. And you see that we get a very good agreement between the direct measurement of the temperature in the disk and with a comparison with a model that would fit the CO map. And I refer you to the talk by Jenny Callahan, where she's basically doing a similar analysis for HD 163.293 using the maps data. And a very interesting thing is that Kees Dulmont proposed to extend this method basically and to measure the temperature in between the upper and the lower surface. So basically measure in the midplane of the disk. And he was able to reach a temperature which is around 20 Kelvin. So basically very close to what we expect the CO freeze-out temperature to be. So by adding this method, we can also add like an extra layer very close to the midplane where we can also measure the gas temperature. And a complementary method that has been developed by Richard Teague, and which is very powerful, is basically using line stacking. So here you have a schematic that of a disk that's inclined, and if you take points along one orbit in the disk, all those points, they'll have the same spectrum, except it will be shifted in velocity because the projected velocity of each of these points is different. So Richard's idea was basically to shift back these 3 points to the same velocity. And because we know what we expect for the rotational velocity of the disk, he can have a model of the disk where he has a model of this rotational velocity and basically try to fit for the rotational velocity to basically shift all those lines so that he minimize the dispersion between all those points. And that's what he has been doing. And one of the main advantages of this method is that because he's combining different pixels and different spectra, he's basically oversampling in velocity the line, and he gets a much better accuracy on the velocity that he can derive, just because he has so many more points that are sampling the line. And he even extended this method to reconstruct the 3D velocity field, because if you assume that at each point in the disk your velocity is not only azimuthal, but you could also have radial and vertical component, because the projection effect when you move along the orbit are different for the radial and the azimuthal velocity, you can basically disentangle the two components. So your projected velocity toward that you detect, it's going to be the systemic velocity plus the rotational velocity times the cosine, and the radial velocity times the sine, plus the vertical velocity, which is the same for all the 3 pixels. And because those two terms are basically orthogonals, you can fit the two together and reconstruct both the azimuthal and the radial velocity. And the residual at the end will give him just the vertical velocity. And this is the kind of result you can obtain, for example. So I've cut some very interesting part in this figure, and I'll show it later. But what he detected in that in the disk of HG163 is that at large radius, he finds some disk wind, like some outward motion of in the disk that could be consistent with a disk wind. So now I'm going to move to the second part, where I'm going to discuss how we detect the turbulence and how we constrain the turbulent motion in the disk. And in particular, Alma has put very strong constraint, and the main conclusion is that the turbulence, at least in most disks, is very weak. So turbulence is a key process, and it controls many physical processes in the disk. So it's going to control the disk accretion and the angular momentum transport. It's going to also impact the dust evolution, the collision, and the growth of the dust grain, and then of the planetesimal. It's going to impact the ability of the disk to form substructure, the way the planets in the disk are going to accrete and open gaps. So I refer you to, there's a few talks on all this subject, and I recommend you to have a look. And most of this work has been done by looking at individual channel maps. So this is an example done by Kevin Flaherty, and I recommend you to have a look at his talk where he explains in detail how he's doing all this fitting. But basically what he's doing is taking channel maps of given molecules, and he's basically fitting a model in the UV plane using a Markov chain Monte Carlo to try to reconstruct the turbulent velocity in the disk. So he has a model that has different parameters, and he's basically marginalizing over every parameter except the turbulent velocity to derive some constraint on the velocity. There's some slightly different method, for example, developed by Stéphane Guillotot and Richard Teague, which are combining two molecules with different molecular weights, but the conclusion are the same. And in all those disks where those type of analysis has been done, the turbulence level and the turbulent velocity are much smaller than order of few percent upper limit of the sound speed. And if you translate that into an alpha viscosity, that would give alpha lower than 10 to the -3. The only exception is GM tau, which may be because the disk is more ionized. And I again refer you to the talk by Kevin, where he's discussing this in more detail. So all these measurements are very exciting because they put strong constraint on the turbulent velocity, but they're limited in a way, and this is basically the lowest we could reach because they're limited by the flux calibration of ALMA, which is around 3% in the base case. Another constraint that we got on the turbulence is using the ring. So it's not kinematics, but because it's a Shelto, I had to put it in this talk. And the main thing is that if you look at Shelto and you look at the gap, the width of the gap is not varying in azimuth. And if you imagine that you have rings that are vertically extended, you would expect the width of the gap to be narrower along the semi-major axis because the two rings are going to overlap with each other due to projection effect. And we don't see that at all in H-Shelto. And so we did some modeling, and to get this kind of result, we need the scale height of the emitting grains to be roughly 1 AU, sorry, at the radius of 100 AU. So we basically, the dust has an aspect ratio of 1/100, so it's 10 times flatter than what we would expect for the gas. And I would also refer you to some talk by Jiang Bi and Mario Floch, who discuss this in a bit more detail. And again, this is not kinematics, but I had to show it because these images are beautiful. So it's work done by Marion Villeneuve, where she has been observing agent disk with ALMA. And she detected the same thing. You have the HST images that you see it, and at the same scale, you have the ALMA images. So the HST imaging are looking at the small grain that's scattered light, while at ALMA, we're seeing like some millimeter grains. And we see that in every single case, the millimeter disk is much flatter and is right in the middle of the dark lane that's seen in scattered light. So we clearly see that the millimeter grains are settling in the midplane. So this strong constraint on the amount of turbulence, that we have turbulence lower than 10 to the -3, are in contradiction with the prediction of the main theory that was believed to control the accretion and the transport of angular momentum and the magnetorotational instability, because the prediction from those models are around 0.3 to 0.8 of the sound speed, sorry. And the only way to get this MRI to work and to produce turbulent velocities that would be consistent with the observation is to have a very weak magnetic field and a weak ionization. And I refer you to the work by Jack Simon, where he has been studying this in a lot of detail. So in turn, what this did is that it revived alternative theory for the transport of angular momentum in disk, and in particular the wind-driven accretion theory. And it led also to the development of non-ideal MHD models and pure hydrodynamic model like the VSI, the vertical shear instability. And I refer you to paper by Antoine Riols and Mario Floch, where they compare those various models. And the main conclusion, from what I can tell, because I'm not an expert at all in this, is that the most successful models so far are the models that include the non-ideal MHD effect, not the pure hydrodynamical models. But I refer you to the review by Vladimir Lara and Geoffroy Le Sur on all this turbulence discussion. I'll move on to the next subject that I think is really important and we need to really consider when we look at planet formation. It's a large-scale gas flow. And for that, I'll start with a simulation that Matthew Bate did a couple of years ago, where he has a molecular cloud that's basically collapsing and forming filament. And inside those filaments, you'll have stars that form and interact with each other. And you see that the flow of gas is falling onto the star. It's interacting with each other, ejecting, exchanging gas, truncating their disk. And the very exciting thing with ALMA is that we're starting to see all those effects, those multiple accretion events from different directions. All of that has been observed with ALMA. And I'll try to show you this kind of results. So basically, what we need to consider is that when we look at planet formation, instead of looking at a disk that's isolated, we need to think of our disk in this kind of environment where they have been interacting with other disks and with the cloud surrounding for a long time. And I think one of the most spectacular example of this kind of structure in velocity is the work by Felipe Alves, where we see a disk where you see clearly the Keplerian rotation, and you see two big filaments that are like feeding the disk. And one of the very exciting things is that if you look at the continuum, the disk is basically seeing a joint, but you see that you have a gap that so the disk is already very structured, what is still feeding from the molecular cloud and the via filaments or like streamers. So it's a very interesting and surprising image, because we clearly see that planet formation and star formation might be happening at the same time. And it's a similar thing with HLTO, for example. So it's work by Yen et al., where by looking at the HCO plus, you can see that there's like filament or streamer of material falling onto the disk, and it's clearly seeing in velocity here, where you have the moment one map, that the material is falling onto the disk. And this could be reminiscent of a simulation done by Keith Dullman, what he calls the cloudlet capture mechanism, where you have a star that can wander through the molecular cloud and capture a slightly denser region, and that would produce this kind of effect. And that's what we might be seeing in those two disks, HD100 and Eber-Riga. It's very reminiscent of what we're detecting with ALMA. And I refer to you to the talk by Michael Kufner, where he's discussing all of this in many more detail than what I'm doing. And another very exciting thing that has been published earlier this year is the work by Jen Huang on the RU loop, and I refer you to a talk which she explained all of that in great detail. And it's very interesting. So here you have scatter light images and continuum images at the same scale as the CO map. So these images have structure inside them, but we don't see them at that scale. But what's very surprising is there's this very large scale CO emission. And if you look at the velocity, it's clearly non-Keplerian. And there's like at least 5 spirals that have been detected. So it's not completely clear what it is. Are we observing like gravitational instabilities that are forming the spiral arms? Are we witnessing cloud fragment that has been unfolding onto the star, or is it the result of a flyby? There could be many possibilities, but it's very interesting picture to keep in mind when we're trying to understand planet formation. And another very interesting object is Elias 227, which here you have the continuum image with very famous two spiral arms that were detected by Laura Perez, and this is a D-sharp image, where on top of these spiral arms, you also see that there's a gap. And I refer you to the talk by Teresa Paneke, where I took just a screenshot of a talk, and you see that the velocity field, so these are the 13C0 and C18O channel maps, you see that his isovelocity curve that I was describing earlier are completely distorted everywhere in the disk. So the disk is clearly non-Keplerian, and there's like non-Keplerian motion on large scale across the whole disk. And it's very reminiscent of the prediction from gravitational instability that have been done by Cassandra Hall, for example. So here, Cassandra run hydrodynamical models of a self-gravitating disk, where the disk is forming spirals, and you also have dust trapping in those spirals. But those big spirals have a strong non-Keplerian velocity that we can detect in the channel map. And the main feature of these gravitational instability wiggles are that they're seen everywhere in the disk, which will be opposite to what you would see, for example, in the case of an embedded planet. And what we detect in the channel map are really like velocity effects due to the spirals, because when Cassandra forced the velocity to be Keplerian, but keeping the same density, you don't see anything. So it's really velocity that we're detecting in these GI wiggles. I'll move on to the next point that I would like to discuss, and I'll be very quick because Nicolas Coelho, I think, is going to discuss all of that in many details. But I would like to at least mention the kinematic aspect of that, and in particular, what we can learn from the velocity field in those events. So we have been starting to see many flybys, so stars that are interacting and exchanging materials. So you have AS205 that has been observed with D-sharp, a paper by Nicolas Kurtovic. And you also have UXTO, a paper by François Ménard. And in both cases, you see that you have the two objects that are exchanging material via a bridge. And this is consistent with a model of a flyby that one of the stars would come around the primary and steal some material from the disk. And interestingly, the velocity field, of course, are very complex around this object. So this is a channel map for AS205, and you see like you have spiral arms, like double spiral arms, you have exchange of material between the two components. And similarly for UXTO, you have the integrated CO map, and you also have like very non-Keplerian velocity field with the two disks that are non-aligned. You have a stream of material here that appear between the two objects. So it's very exciting. Of course, it requires detailed modeling to understand everything, but it's, I think, important to keep in mind that the disks that we're looking at might be this kind of objects that have been interacting and being disturbed by neighboring stars. And I move on to a slightly different type of the kinematic and multiple star interaction. And I would like to discuss a bit the origin of the cavity in what's called the transition disk, and in particular in the transition disk with large cavities. So transition disks were initially defined as having a dip in the ACD in the near infrared, which was assumed to be due to the fact to a lack of material in the central part of the disk. So they were believed initially to be a transition phase between the young gas-rich protoplanetary disk and the debris disk. But it became relatively clear early on that some of those debris disks could also be circumbinary disks. And I think ALMA has given the definite evidence for this kind of circumbinary disk in at least some of the cases. So here's the data for HD 142527, and here's the observation that has been taken by Simon Casassis. And we see the continuum when you detect the cavity, and you see that the velocity field is clearly non-Keplerian. So this is a zoom in the central part, and you see like you have a twist in the kinematics. So this is the moment one map, and if the disk was clearly Keplerian, you expect the green line basically to be a straight line. So this twist there is clearly indicating that the motion is not Keplerian. It could be due to many effects, like an inclined disk, streamers in the cavity, but at least it indicates that something is not is strongly disturbed inside the cavity. And Daniel Price, and I refer to his talk, has run a model where he's basically putting a binary which was detected in particular. So he's using the orbit that has been, for example, by Sylvestre Lacour. So we know the orbit of the binary, and if you put the binary inside his model, it can basically reproduce all the features that we observe. The asymmetric horseshoe in the dust continuum, spiral arms that has been detected. We also know that there's an inner disk that's casting shadow. All of that is reproduced in the model. So it's a very simple explanation for all these features that we're detecting in this kind of transition disk with large cavity. And there's been more recent evidence of non-Keplerian motion in the disk. So this is the spiral that were detected at large scale by Valentin Christian in a few years back. And this is new observation that has been in a paper by Himanshi Garg, and I refer you to a talk. And basically what we're seeing is that if you look at a specific channel map, you see that instead of having the emission around the loop, you have some extension at the location of the spiral. So we see that the emission is coming from region where you expect the velocity to be higher. So we basically have spirals that are super Keplerian or are coming toward us. So they appear faster than they should be. And conversely, if you look in between the spiral, you see that the emission is extending in the other part along the semi-major axis of this, which suggests that either those motion are like sub-Keplerian or they're going down towards the midplane. So I think the most interesting aspect of that is that these spirals are very large scale, and they're clearly not just spiral in intensity or in density. They're clearly velocity feature, and they're probably connected somehow to the central binary. But we see them extending to very large scale, up to 300 AU, which is much bigger than the size of the binary. And this transition disk with big cavity, most of them displays this kind of non-Keplerian kinematics. So for example, you have data from a paper by Josh Calcino on IRS 48, sorry, I didn't put the name. But we clearly see that the kinematic is non-Keplerian, and this is very well reproduced by a model if you put a binary that's eccentric and inclined in the model. And this is the same kind of result for Ebe Orega, work by Pedro Poblete, and I refer you to his talk where we also, the presence of a massive companion is inferred to explain the features that we detect, in particular in kinematics. And I also refer you to the talk by Tane Curry, where is discussing some possible companion in this object. And finally, I'd like to move to the last part of my talk, which is the kinematic of planet-disk interaction. And before I do anything, I'd like to put a poll. So what do you think is a detection of a planet? So we've recently found some kinematic detection of planet. Is that a robust detection or not? One of these detection was defined as a new method for detecting planet by NASA. Is it valid or not? So I'd like to know your opinion, and if you could please answer to the poll, I'd be very interested to know the result. So detecting planet in young disk is very difficult because the normal method cannot be applied. If you have a disk that's edge on and you would like to do transit and radial velocity, the star is blocked by the disk. So you're not able to do that. And if you try to do imaging, you're basically contaminated by the disk. And I refer you to the talk by Ten Curry, which is discussing how difficult it is to image a disk, and also by Valentin Christian and Antonio Garofini. So when you have a planet embedded in the disk, you expect many signatures, and in particular, all of those signatures will have velocity counterpart. And one of the first one is that when you carve a gap, you expect velocity modulation due to the gap. The planet is going to general spiral wakes, which will also appear in velocity. You expect to have vertical flow, meridional flows, which are schematically represented here, potentially increase in turbulent motion. We might have a circumplanetary disk, and we could also have buoyancy spirals that are detected. So I'll start with the pressure gradient. So this is work that has done by Richard Hicks. So if you have a gap at the location of the planet, because you have a maximum and a minimum pressure gradient, you'll have a deviation in velocity. And by using the method that I presented earlier, is able to measure the rotation velocity. And so you have all the data that has been extracted from HD 163296, and you see that he finds minima that correspond to the location of planet, and he feeds that with a model that match very well the observation. So basically, what he's telling us is that there's probably like 3 planets embedded in the disk that are creating this pressure gradient at the location of the gap. He did the same kind of exercise for AS209, where you can see the same thing, where you have variation in velocity that correspond to the gap. And interestingly, there's a shift between the millimeter and the near infrared, which may suggest that there's a variation in the pressure gradient with the altitude. And as I mentioned earlier, because you can disentangle between the different components, Richard is able to reconstruct the full velocity field. So the 3 velocity components, the rotational velocity, the radial velocity, and the vertical velocity. And he sees deviation in all of them. And this is basically the main result of his paper that he published in Nature last year, is that at the location of each gap and at further outside, you have this variation in Keplerian velocity in the azimuthal direction, but you also have, very interestingly, like meridional flow. So you basically see the gas falling inside the gap due to the viscous evolution of the disk. So as the planet carves the gap, the gas is trying to go back inside and filling up the gas. And this is this kind of motion that he was able to detect thanks to this advanced method of combining the velocity in different directions. This is data that have been taken from Richard's talk, and it's done from the MAPS collaboration. And so this is NWC 480, where it detects spiral again in velocity and also in temperature. And this is similar to the work he has been doing on TW Hydra, where he detects again spirals. And all of these spirals, in both cases, they have very low pitch angles. So one of the explanations that's pushed by Jian Bei, and I refer you to his talk, is that there could be buoyancy spirals because they're not consistent with the spiral wakes that you expect from the spirals. And those buoyancy spirals, they generate much more important vertical motion, which what we may be detecting in the case of TW Hydra and NWC 480. And another prediction from the presence of a planet in the disk is the presence of a kink and of a CPD. So this is work by Sebastian Perez, who is run hydrodynamic simulation and making synthetic map. And you see that if you embed a planet, you expect a distortion in the channel map, which what we call a kink, and you see it there. And potentially you might be able to detect the CPD, but this has not been detected so far. But this kind of kink have been detected. And this is one of them that we've been detected in HD 163. And the very interesting thing is that this kink is localized. So we see a deviation in one of the channels. But if you look on the other side of the disk, the emission is completely smooth. So you have a nice butterfly pattern with no disturbance. So because the deviation is localized, it means that the body there's a body inside perturbating it, and it's very likely to be a planet. And the amplitude of the deviation are around 15%, sorry, of the Keplerian velocity. And we can run models to try to reproduce that. Ah, yes, sorry, forgot to mention this velocity kink has been detected in several data sets. So you have the 221 and the 322, and it was redetected by D#, and it was redetected again by the MAPS data, and Richard Ting is preparing a paper on that. So we have been running models to try to reproduce these observations. So we use the phantom code by Daniel Price, and then we plug it into the relative transfer MCFOS, and we run a bunch of models varying the mass of the planet. So at the top, you have the data, and here you have different models where the mass is changing from 1 to 5 Jupiter masses. And basically, by trying to match the amplitude of the kink, we're trying to measure the mass of the planet. And we find that a mass of 2 to 3 Jupiter mass is enough to explain the data. And interestingly, the amplitude of the kink doesn't depend on the viscosity. And I refer you to the talks by Giuseppe Lodato, where he's describing an analytical description of those kink, and we can try to predict and fit the data without having to run models. Another interesting thing is that at the same distance, there was a gap that was detected 20 years ago by Carol Grady in the disks, and it was redetected with re-imaging of the HST data. So the planet would be there right inside the gap seen in scattered light. And this is a second object, HD 97048, where we've detected again a kink. And the interesting thing is that now if you put the planet and you deproject it, the planet would be inside the gap. And it's the same thing as for HD 163. The kink is localized in one channel, and if you look on the other side of the disk, the emission is completely smooth. So again, this suggests that it's something inside the disk perturbating the velocity. So we've done the same kind of analysis where we run hydrodynamical models, and we run also with different grain size. And I think one of the interesting things is that, again, to try to fit the data, we need something that's around 2 Jupiter masses to reproduce the amplitude of the deviation within the data. But to be able to reproduce simultaneously the CO map and the continuum, we need the dust grain that emit the most in the continuum to have a Stokes number around 10 to the minus 2. So much smaller than the Stokes of 1 that you would expect. In that case, the rings are too narrow to match the data. And that probably suggests that the dust grain that we're seeing are porous. And I refer you to the talk by Akimasa just after me, which is by using polarization, we might have also some indication that the dust grain are porous in the disk. And another interesting thing is that we look back at the D# data and we find many of these deviation that could correspond to planets. And when we deprojected it, they all fall inside the gap or at the tip of a spiral in the D# data. So the D# data was not designed to look for kinematics. So you can see that the data set are very noisy. So all this detection will need to be confirmed, but it's very promising that there's probably many more of this velocity deviation corresponding to planets that we can expect to detect in the next few years. And one of these interesting features has been detected by Sebastian Perez and Simon Casassus, what they call a Doppler flip. So it's in the disk around HD 100 546, where if you have a planet embedded in the disk, you expect those two spiral waves with sign reversal in the velocity field, and that's what they see there. The surprising thing, though, is that this flip, it's Doppler flip, is on top of the continuum. So if it's created by the planet, would mean the planet might be inside the continuum ring. So it's not completely clear yet what it is, but it's definitely a strong feature in velocity that's very interesting to explore. And I'll finish with the slide that I borrowed from Richard Ting. So this is the MAPS observation of HD 163296. And this is the planet that we detected with a kink. And you see that very interestingly, even with very good data like MAPS, it doesn't appear as a Doppler flip. And I think it's because the Doppler flip is considered, is only considering the azimuthal velocity. And what we're seeing here is a contribution from both the azimuthal velocities, the vertical flow inside the gap potentially, and also the radial velocity that we might be seeing. And interestingly, this is a prediction we did of what it would look like, and it's kind of very similar. You have a strong redshifted emission with a spiral extending. And I refer you again to the talk by Richard. He finds many other features in this disk, so it's a very interesting target to follow up. So I'll just conclude. Just briefly, we have many kinematic evidence that the star formation is happening at the same time as planet formation. In some cases, we have detected planet, and in most of those cases, the planets are located inside the gaps. So it's a strong indication that at least some of the gaps that we're seeing are carved by planets. And I think we're only seeing the tip of the iceberg in terms of planet discovery so far. We've detected very massive planets very far out, but I expect that many more closer in, smaller planets will be detected in the next few years. Thank you very much.
Thank you very much, Christophe, for your very nice comprehensive review. And before going into the Q&A session, we are looking at the results of the poll. If the question was, what is required for the embedded planet detection to be robust? So it looks like more than 50% of participants want to get 2 independent detections rather than 3+ independent detections. So Christophe, yeah, do you have any comments about this poll results?
Oh no, I mostly agree with that. Yeah, I think it's the kinematic is very complementary to the direct imaging. So ideally, you want a kinematic detection to get a planet mass, and then an image to try to calibrate in flux and potentially put some constraints on what kind of planet do you have. Is it a hot start, a cold start, a warm start model? Is there a CPD or not? So I think, yeah, I agree with the result.
Okay, so your answer is the kinematics and maybe imaging. Those 2 combinations.
Yes,
would be the best. Okay.
I mean, some of the kinematic feature, in particular HG163, I'm very convinced that it's a planet, but the problem is that they're very difficult to detect in direct imaging.
Mm-hmm. Okay, thank you very much. So then we can go to the questions and answers session. So for example, if I pick up the most voted one. So, okay, so Christophe, the first question is that, are the measured radial gas velocities consistent with the classically measured accretion rates?
Oh, I don't think we've been able to measure is that meant to be the accretion on the star? Because I don't think we've been able to measure the radial velocity corresponding to the accretion onto the star.
Yeah, for example, Brett, you have shown us about the estimate of the alpha parameter, for example, and yes. That is clearly inconsistent with the accretion rates onto the star. So, and another maybe interesting comparison would be the accretion rates and some kind of insights into the accretion flow, within the gas, within the disk.
Yes, I mean, one of the problems is that when we convert the constraint we get from the turbulent velocity or the dust settling, and we try to convert that into an alpha value, it assumes that we can define an alpha, which means we have which is not the case. For example, if I refer you to the talk by Mario Flock, where he's discussing the VSI, where you find that the turbulent velocity could be consistent with what we detect, but it doesn't produce any settling. So it's the 2 alpha values that we would get from those 2 estimates would be very different. So we have to be careful when we discuss the alpha value, because the meaning might not be that. There might not be so much meaning to it.
Okay, thank you. Then go to next question. This is also most voted from Jake Simon. So I'm a bit confused. How can you see the backside of the disk if the CO emission from that side has to pass through the optically thick front side?
Are we able to do that due to projection effect? So because in the midplane, most of the CO is frozen out, the midplane is transparent. And when you have two surfaces, if they're inclined, they will be shifted compared to each other. So basically, the backside is going through the transparent part of the disk. If your disk was polon, for example, you would not be able to see the backside.
Okay, thank you. Okay, so then we also go to the next one. Okay, so this will be interesting one. This is about the meridional flows. So are these meridional flows expected in any type of gap in the gas or only in the planet-induced gas?
I think they would be expected in any type of gap.
So it's not the unique evidence of that.
Basically, the viscous evolution of the disk. If you carve a gap, whatever the mechanism is, the viscosity will try to fill it back up. As far as I know, most of the model have been with planets, and the advantage of a planet is you expect you might have an azimuthal dependence, so we might be able to put more constraint on that if we find that the azimuthal flow is stronger in some specific part of the disk compared to other one. Okay. We might be able to differentiate at some point.
Mm-hmm. Thank you very much. And we have 5 minutes, so maybe go to another one. Okay, so this is a purely observational question. So for embedded or younger objects that suffer from lots of cloud contamination, are disk kinematics studies still feasible?
Probably not. So that's one of the main problem. Ideally, you want to use a bright line that's very easy to observe, like 12 CO, which was what was in D-sharp, for example. But in most of the D-sharp sources, half of the data is missing just because of cloud extinction or filtering by the interferometer. So it's always a compromise between having a line that's very bright or could be contaminated. Unfortunately, at very embedded stages, it will be very difficult.
Right. Okay, thanks. Then go to the next one. Okay, so I'm gonna pick this one. Okay, so is it possible to distinguish the thermal pressure from self-gravity? Could this be used to measure the surface density profile for massive, maybe class 1 disks? It's maybe a little bit difficult one.
The short answer is I don't know. I think the problem with class 1 will be that we will have a hard time to have clean kinematics. So I suspect it will be difficult. And I mean, if you look back at the paper by Catherine Rosenfeld, she was predicting both effects, the self-gravity and the pressure gradient, and they look different. So technically, we should be able to distinguish, but it's a matter of being able to get the line that might give you the data from which you could do that.
Mm-hmm. Okay, yeah, thank you very much. This will be an interesting, a discussion topic. Okay, so go to different topics. So maybe this would be also interesting. So you have shown us, the extension of the larger scale gas, sometimes with the spiral features or filamentary gas. So the question is that mass supply from larger scale gas can keep the large disk for a long time, which would affect the planet formation in such disks. So the question is that, are they common, or do you see any correlation between the star parameters with the existence of such a large scale extended gas?
The real answer is I don't know. And I don't think there's enough sources for which we have seen this kind of filaments flowing into the protostars to be able to say yet. But the real answer is I don't know.
Right. Maybe we need the sensitivity and also the reasonable spatial resolution and that kind of, a kind of intermediate parameter space from the previous generation observations and also the very high resolution. Right. Okay. Yeah, but this is an interesting question. Okay, thank you very much. And then go to the next most voted one. Okay, so this is about DM tau. You have mentioned yeah, higher turbulence. So the question is, could you mention what are the possible scenarios to explain the higher turbulence in DM tau? You have mentioned the high ionization rate, but yeah, if you have any other
there's
comments.
already a discussion on the Slack channel on that, on the Slack corresponding to Kevin's talk, and I think the most likely explanation, I believe, is that there's for some reason a high ionization. So DM2 doesn't have a wind as far as we know, so maybe the disk is more ionized because the radiation can reach the outer disk more easily. But I don't think Kevin is the person to ask, but I don't think we have the clear idea of why DM2 has such a high turbulent value compared to the other disk. It's still a bit of an enigma, at least in my opinion.
Okay, great, thank you. It's an interesting object. So go to maybe this one. Yes, okay. So about the misalignment in disks, the question is that, is there a possibility to observationally distinguish between the origin of a misalignment in disks?
Well, it depends what misalignment. If you look at transition disk with big cavities, the misalignment is very well explained by the presence of a binary. So, but I guess the key question in that case is, why was it misaligned in the beginning? Is it like multiple accretion events? I don't think we're able to tell really, because it's probably going to depend on the history of the protostar and what happened, and we're only seeing it at one snapshot in time, so I don't think we can.
Okay. All right, so I think we have 15 seconds. Okay, go to the last question. So why is the kink in HD163296 seen clearly in the upper surface of the CO, but not so much in the lower surface?
So it's due to projection effect, and we see the same thing in the model. So it's completely consistent with the planet. If you look at the synthetic map that we produce, we have the same effect due to the orientation, because the two surfaces do not have the same projection towards the observers. It's easier to detect it in the upper surface.
Mm-hmm. Okay, all right. So I think we don't have enough time for questions anymore. So you can, participants, you can always go to the Slack channel named Day 3 Kinematics Dynamics, and you can, put your questions in the Slack channel. Then Christoph will answer your questions. Yeah. And Christoph, yeah, again, many thanks for your very nice embodied talks and answers to many questions. Thank you. Thank you. All right. Okay, so the next embodied talk will be by Akimasa Kataoka-san. Okay, so he is going to talk about the polarization. So please start sharing the screen.
Yes, I will. And okay, can you see this?
Yes.
And can you hear me? Yes, great. Yes, and also, can you see the pointer as well?
Right.
Okay, great. Nice to meet you. First of all, thank you for the organizers for organizing this very nice conference under this difficult situation. I'm very honored to have a review talk here about the millimeter wave polarization in protoplanetary disks. When you hear about polarization, I know what you feel. It's kind of complex and probably it's a bit away from my field. I know, it's same as me. So that's why I'm here to make a review talk on the millimeter wave polarization. So I made this make this talk as intuitive as possible. So I hope you enjoy my talk. So let's start from the history. Before 2015, what had been expected? So which was totally different. In general, in the star-forming regions, the radiative torque alignment has been a great success in explaining the polarization due to the alignment with magnetic fields. So the thermal dust emission is shows the intrinsic polarization perpendicular to the magnetic fields. That's why we can know the direction of the magnetic fields. So these are the predictions. And in the pre-ALMA era, there are many trials, especially by the group led by Meredith Hughes. And finally, a group led by Ian Stevens found 2 sigma detections of millimeter wave polarization from HL tau. That's why HL tau is revolutionary also to the field of polarization. However, it was not expected because the detected polarization infers this magnetic fields. Usually, we rotate the polarization vectors by 90 degrees to infer the direction of magnetic fields. But in this case, as you see, it looks like a edge on disk with toroidal fields, but we know that the inclination of H tau is 45 degrees. So it was kind of a mystery. After ALMA came into play, the situation has been completely changed. So after 2015, there was a dramatic progress in this field. So as you see here, I just picked up 6 disks, which shows millimeter wave polarization. There are many detections with ALMA owing to the high sensitivity and high angular resolutions. But also, there's a big progress in theories as well. One is that the self-scattering, which is a new idea of the origin of the polarization. And also, even if grains are aligned, but probably the direction of the aligned grains may be different from magnetic fields. So I am going to talk about these 3 major developments in the last 5 years. So before going to the details, I would like to motivate you by showing the beautiful ALMA observations by categorizing into 3 categories. So I picked up smooth and inclined disks. For example, many disks show the polarization, which is parallel to the disk minor axis. And the second one is that the azimuthal pattern of the polarization. The third one is the mixture of them. So I think these are the major categories of the detected polarization with ALMA. So one of the motivation is to understand why we see such a morphology in polarization vectors. The other motivation is that to explain is that the wavelength dependence. So as shown by Felipe Alves, the BHP 0711 shows this beautiful polarization pattern, and which is wavelength independent between 0.9 millimeter to 3 millimeters. In contrast, H tau shows this beautiful transition of polarization from 0.9 millimeter to 3 millimeters. So we would also like to understand why some disks shows wavelength dependent polarization and some shows wavelength independent polarizations. So I think I have motivated you to explain these patterns of the observed polarizations. Now we are ready to go to the theories and models that may produce the millimeter wave polarization from protoplanetary disks. Basically, there are 2 major mechanisms which can emit polarization. One is the scattering, the other is the alignment. First, let's get to the scattering. In the case of the infrared scattering, the mechanism is different. So in the case of infrared, the infrared photons are emitted from the central stars, and then it is scattered by dust grains at the surface layer of the disk. That's why we can see the scattered light as polarized emission. However, if you go to the millimeter wavelengths, the situation is very different because the central star is dark at the millimeter wavelengths. That's why the thermal dust emission itself is the light source of the scattering, and dust grains scatter the thermal dust emissions from other dust grains, and they emit scatter light. So that's why we call them as a self-scattering. I would like to explain the mechanisms in details. So here I prepared flashlight here, and please consider this as a thermal dust emission of other dust grains, and I assume here a dust grain. And let's assume that this emission is scattered by this dust grain. And as you see here, the observer is you. So because the line of sight is perpendicular to this screen, so you would see this horizontal polarization because of the scattering. Now, I put another thermal dust emission from the bottom. This also produced this horizontal polarization because of the 90-degree scattering. So as a superposition of them, we still expect horizontal polarizations. Now we add two more flashlights from right and left. These will produce polarization in the vertical direction. And as a superposition of them, the emission is unpolarized, which explains that if the radiation fields are isotropic, then we don't expect any polarizations. In other words, if the radiation has an anisotropy, then we will expect to see polarization, in this case, the vertical polarization as a residual. So now we are ready to apply this theory to disks. So assume that this represents a thermal dust emission. If the thermal dust emission has a tube-like structure, then the thermal emission would be perpendicular to the tube because of the theory that I had explained. Now, I prepared a ring disk. It's a disk. And if we apply this theory to the ring, then the polarization would be perpendicular to the ring direction. So we expect radial polarization if it is due to scattering. If you are very hungry, or if you look or observe a lopsided disk, the situation is similar. Because of that theory, we expect still the radial polarization, as you see. Now, please watch the disk as an edge-on view. In this case, as you apply this, we expect to see the vertical polarization. And please keep this disk in your mind and slightly change the inclination. We still expect the polarization parallel to the minor axis. So as you see, from an inclined disk, we expect to see a polarization parallel to the minor axis. Okay, and of course, these donuts are not enough for publications. So there are many authors trying to reproduce that with radiative transfer calculations. So don't worry. So if you make a radiative transfer calculations for a ring-like disk, we expect radial polarization inside and azimuthal outside. And for the inclined disk, we expect to see the polarization parallel to the disk minor axis. Okay, these are the expectations from the self-scattering theory for the polarization morphologies. Then what can we learn from self-scattering? Now let's consider the condition that the grains can emit scattering in these polarizations. The one condition is that the high albedo. Albedo represents the efficiency of the scattering. And usually albedo is a kind of a step function as a grain size. If the grain size is large, then this albedo is large. And the transition is at around the wavelengths. The grain size is equal to the wavelengths. But we need another condition to be satisfied, which is the polarization. Even if the emission is scattered, if the emission is not polarized, then we cannot detect polarization. And this polarization at single scattering has an opposite function to the albedo. So we need small grains for the polarization to be efficient. That's why the scattering in this polarization is detectable only when the grain size is comparable to the wavelengths. And of course, here I assume a spherical dust grain, and I will discuss the non-spherical grains later. And with this in your mind, we can predict the polarization as a function of the grain size. So, for example, if the grain size is 1 millimeter, then we will detect polarization due to scattering at the wavelengths of 7 millimeter and slightly with 3 millimeters, and non-detection is expected for the 0.9 millimeter. This was the expectations for the self-scattering in this polarization. In summary, we need anisotropies of the radiation fields and the very sweet grain size. Only with, in the case with these conditions satisfied, we would expect to see the polarization due to scattering. Okay, now we move on to this, the other polarization mechanisms, which is the grain alignment. So in the interstellar medium, the direction of the alignment is usually the magnetic fields. But in the case of the protoplanetary disks, situation is completely different. So I'm going to discuss these three possibilities of the direction of the grain alignment. First of all, let's start with the magnetic fields. So usually we assume that the magnetic fields are in a toroidal direction, which is in the azimuthal direction. And if it is the case, because the polarization is perpendicular to the grain, perpendicular to the magnetic field directions, so we expect such a radial polarization patterns, as you see here. So the prediction is easy. If the grains are aligned with the magnetic fields, we expect radial pattern in polarization vectors. But Ryo Tazaki proposed that probably grains are not aligned with the direction to the magnetic fields in the midplane of the protoplanetary disks. He calculated the precession timescales of the grain as a function of the grain radius. In short, the shortest timescale dominates the phenomena. So please look at the yellow shaded region. So with some specific parameters, for example, in this case, very small grains are aligned with the magnetic fields. But large grains, for example, larger than 100 micron size, they are aligned with the radiation flux. And at the midplane of the protoplanetary disks, the radiation flux is always from inside toward outside. So his prediction is that grains larger than 100 micron aligned with the radiation flux, and they emit this azimuthal pattern in polarization. I will also like to mention that the third mechanism, which is the mechanical alignment. Unfortunately, the microphysics is missing, but the mechanism itself is very simple. If there is a gas flow against a dust grain, then they can be aligned with the gas flow. For example, in this case, the major axis is parallel to the gas flow on the dust. But we have to be careful because the direction of the relative velocity between gas and dust should be considered with the Stokes numbers. For example, if the grains are drifting, the relative velocity between gas and dust is very different from the case of the small dust grains. in short, for example, if the grains are very coupled to the gas, we expect this azimuthal pattern. But if the grains are decoupled from the gas, then we expect this like a spiral pattern. But I would like to emphasize that the microphysics is missing. So to summarize the expectations of the polarization morphologies, here I show the summary. So in the case of the self-scattering, it's easy. The polarization vectors should be parallel to the disk minor axis. In case of alignment, it depends on the direction that grains are aligned. For example, if the grains are aligned with the magnetic fields, then we expect this radial pattern. And if they are aligned with the radiation flux, then we expect this azimuthal pattern. And if they are aligned with the gas flow, it depends on the Stokes numbers. And in addition, importantly, the self-scattering in this polarization is strongly wavelength dependent, as I explained with the albedo and the polarization efficiency. On the other hand, the polarization morphologies do not so much wavelength dependent in case of the alignments. So these are the summary and predictions of the theories and modelings. Okay, so now we came back to here. So I wish that you still remember that the motivations I showed before, and now we have the tools to interpret the observations. So now here I would like to make a basic interpretations of the major polarization morphologies of protomagnetic disks. Okay. So motivation one. So I have, as I showed before, I have categorized the polarization morphologies of smooth inclined disks into 3 categories. One is that the polarization parallel to the disk minor axis, and obviously it's due to self-scattering. I believe you are convinced now. In the case of azimuthal polarization, the situation is still complex. Obviously, it's not due to alignment. It's not due to self-scattering, but there are still possibilities of alignment with radiation flux or gas flow. The third one is mixture, and usually we see polarization parallel to the minor axis at the center of the disk, so which would be due to self-scattering. But for the outer part, it's probably due to alignment or due to self-scattering. And please check the talk by Francesca Bacciotti for the more detailed discussions on the interpretation of the DG tau and C level tau. So the other interesting phenomena that I have explained was the wavelength dependence of the polarizations. So in case of BHP07, obviously it's not scattering. It should be alignment. But still, we do not know much if they are aligned with the direction of the magnetic fields or due to the gas flow. In the case of HL tau, the short or the submillimeter wavelength is due to self-scattering. But for the longer wavelengths, it's due to alignment, and we see transitions. So these are the interpretations from the morphologies. Okay, I think I'm going well in the schedule. So now we have kind of tools to interpret the basics of the polarization. And here, from now, I would like to make some implications and discussions to planet formation. Okay, first of all, the grain size. So because this is a conference for HL tau, so let's start from HL tau. So as we know, that the HL tau shows very beautiful substructures, and also they have similar morphologies in the continuum between 0.9 millimeter and 3 millimeters. However, we see a beautiful transition from in the case of polarization. And if we take a summation of the Stokes Q and U component, we can define the total polarization fraction, or assume that we observe the disk with a very large beam size, or only one beam. In that case, self-scattering component still remains because they are in basically the same direction. However, azimuthal pattern will be canceled out if the beam is very large. So with this technique, we can extract the information of the self-scattering. And this figure shows the total polarization as a function of the wavelengths. So as you see here, the polarization is a decreasing function of the wavelengths. And with changing the grain size, only when we set the grain size to be 70 micron, or roughly speaking, 100 micron, we can fit the HL tau polarization, which means that grain size in HL tau would be 100 micron. There are many detections of self-scattering polarization at the wavelengths of 0.9 millimeter. Of course, we need to make a multi-wavelength analysis, but even with this one band polarization, for the 0.9 millimeter polarization to be effective, we need 100 micron size grains. So the question is, do disks have dust grains with a size of 100 micron? Of course, this is inconsistent with the analysis of the spectral indices. So as we heard from Ilaria Pascucci yesterday, there are many analyses of the spectral indices at the millimeter wavelengths, which shows that the grains are grown to millimeter or centimeters. So basic idea is here. So this beta represents the steepness of the dust opacity at the millimeter wavelengths. And if you check the millimeter colors of protoplanetary disks, the alpha value is between 2 to 3, which means that the beta value in the opacity index would be between 0 to 1. So that's why we need millimeter to centimeter grains. And obviously, this is much larger than the implication from the polarization. So, so if we make a synthetic observations with a kind of normal assumptions, what happens? So in this case, they put a planet at 60 AUs and they let the dust grains grow and drift. What happens is that the dust grains make a ring by the pressure trap, and it shows a bright emission at the ring here. But if you make a synthetic observations of this disk, we expect this polarization patterns. So this is a kind of infinite spatial resolution. So that's why we see this slight polarization rings at 3 locations, which corresponds to where the grain size, a maximum grain size is around 100 micron. But if we convolve this with a beam, then the expected polarization degree is too low to be detected. So if we make a prediction from a pressure trapping scenario, then the polarization is not expected to be detected. So that's why we need some ideas to solve this inconsistency. One idea is to really make the grain size to be 100 micron. So the Okuzumi and Hazaki proposed one idea to make this happen. So they need two conditions. One is that assuming a dust grains to be non-sticky or fragile. It can be achieved by, for example, assuming the dust grains are covered by CO2 mantles, which makes the dust grains to be fragile. And if they are fragile, they are disrupted by collisions. And that's why they can achieve small grains such as 100 micron. But they also need flat radial surface density distributions, because the fragmentation requires the Stokes number to be constant in radially. And for the grain size to be constant, we need the gas surface density to be constant in radial directions. That's why if we assume these conditions, we can achieve 100 micron size grains, and we can reproduce the HO tau polarization in this case. Okay, this may be the case. Another idea is to make the disk optically thick. So in this case, Satoshi Ohashi and his colleagues modeled the IRS-48. So they modeled these three observations. One is the short wavelength Stokes I emission. Another one is the polarized emission at the band 7 with ALMA, and the 8 millimeter Stokes I emission. So if there is no polarization, then the modeling is very easy. If the emission is bright at the 8 or 9 millimeters, then we usually assume the grains to be bigger, which makes the opacity slope to be flatter. Then it's easy to explain both the short wavelengths and long wavelengths. However, to explain the detected polarization at the 0.9 millimeter, we need small grains. The idea is that the making this disk very optically thick. In the best fit model of them shows the optical depths at 0.9 millimeter to be 7.3. In this case, they can assume 100 micron size grains, and they can reproduce the polarization as well as the long wavelength observations. So as you see, one of the key observations is the long wavelength observations, and we expect a lot on VLA and also the next generation in VLA as well. Okay, this idea can be also applied to the substructures. So in the case of HD 163296, we know that as a part of the D-sharp project, we see these nice rings in the continuum emission. And I think so far, this is the only case that we see the polarimetric substructures. One reason is that we need very, very high sensitivity to detect polarization, because it's only 1% or around 1% of the continuum emission. So that's why usually we set the spatial resolution to be bigger than usual. But this is the only case that we know the polarimetric substructures. And okay, I think yes. Sorry, sorry. And yes, so Daniel Lin and his colleagues modeled this HD 163296 with 100 micron size grains, but changing the optical depths. So as you see here with the dashed black line, in their model, the spectral indices is going up to 4 at the gaps and going down to 1.5 at the rings. It's simply because of the optical depth effect. So if it is optically thick, it's around 2, and if it is optically thin, it's around 4. Oops. And combining these with the observed beam, they can reproduce the observed spectral indices profile in radial directions. And if they assume 100 microsize grains, then they can also reproduce the polarization detected with ALMA. So combining, probably this is the one solution for solving the inconsistency between the spectral indices and the polarization for the grain size. Now it's slightly off topic from the polarization, but I would like to emphasize the importance of the scattering, but even at the continuum emission. And it's always good to go back to the old papers. For example, in this case, this paper is published 27 years ago. So in the appendix of this paper, it's already predicted. So in this case, they assumed a optically thick slab and changing the albedo and to see what happens for the continuum emission. So for example, if the optical depth is as high as, for example, 10, then the flux is only 60% of the case of no scattering. This happens because the scattering makes the disk fainter, and these are also discovered by these authors. This is very important, and for H.L. Tao, with using these four bands, Carlos Carrasco Gonzalez made a full analysis with including the effect of the scattering. And what they have found was that the optical depth at 0.9 millimeter is as high as 10 at rings and around 5 to 6 at gaps. So the H.L. Tau may be really optically thick. So please check the talks by Anibal Ciela for the similar analysis, but for the MAPS data. That's fantastic. And also Enrique Macias for the analysis on tetrahedra. One important message here is that probably we have underestimated the dust mass at the very optically thick regions of protoplanetary disks. For example, by analyzing the central part of tetrahedra, the mass was underestimated by a factor of 20 or more. So, but this can be the case for the optically thick rings as well. All right, so okay, so I had discussed on the self-scattering in this polarization and the effect of the scattering even onto the continuum emission. Now I came back to the polarization and especially on the alignment-induced polarization. So let's get back to H.L. Tau as always. As you see, as we know, polarization has a so H.L. Tau shows the beautiful transition from 0.9 millimeter to 3 millimeters. And I have explained that why the self-scattering is a decreasing function of the wavelengths. But I have not explained why we see alignment-induced polarization at 3 millimeter, but we don't see alignment-induced polarization at 0.9 millimeter, which may indicate that even the alignment in this polarization is wavelength dependent. So to understand this, I made a very simple cartoon. So this represents the grain size and the corresponding polarization orientations. Usually, we consider the grain size to be much smaller than the wavelengths. In that case, it's very intuitive. So the polarization orientation of the intrinsic polarization is parallel to the major axis of the dust grains. Okay, that's very simple. On the other hand, if the grain size is much larger than the wavelengths, then we don't expect any polarization from the intrinsic emission. this is because that the wavelength is very small, so the photons does not know the size of the grains. So we don't expect any polarization. Even more interesting, if the grain size is comparable to the wavelength, then the orientation of the polarization flips by 90 degrees. So which means that polarization is perpendicular to the major axis, which is also called as a Mie regime. And this is also discussed by many authors, but here I picked up a paper by Vincent Guillot. So they have proposed that they have calculated that the intrinsic polarization as a function of the wavelengths. And these numbers represents the grain size. So we usually expect the polarization, intrinsic polarization, parallel to the dust major axis. And these 3 data points are taken from these observations by Felipe Alves. So polarization vectors looks wavelength independent, but the polarization fraction is slightly wavelength dependent. To reproduce them with a kind of normal polarization, the function is too steep to reproduce. However, if you go down to this figure, this negative value of polarization means the flip of the orientation of the polarization. In this case, the 1 millimeter grains are roughly explaining the wavelength dependence of the polarization fraction. This is very interesting. If this is the case, then the inferred direction of the grain, the major axis of the grain, is 90 degrees wrong from the previous interpretations. If this is the case for HL tau, for example, then maybe grains are aligned with the magnetic fields and polarization is parallel to them. So this may be the possibility. Another interesting and detailed analysis is on the azimuthal pattern of the polarization. So Haifeng Yan and his colleagues pointed out that radiation flux alignment cannot explain the observed azimuthal pattern of the polarization. So as I explained, the 3 millimeter polarization of HL tau shows azimuthal pattern. And I have explained that this may be due to the alignment in this polarization with the radiation flux. However, these authors pointed out that if this is the case, then the normal direction of the polarization should be always toward the central star. However, as you see, it looks like an elliptical pattern. So to reproduce this, radiation flux is not the case, but we need the grain alignment with the gas flow. However, as I explained before, if for the gas flow alignment to be the case, we need supersonic flow in the disks. And we know that the gas flow is subsonic, so we are kind of stuck here. So probably, so far there's no perfect theory that can explain this azimuthal pattern with the alignment theories. Okay, another recent progress is on the non-spherical grains. So for example, Ryo Tazaki calculated the polarization and also the albedo, which basically represents the expected polarization fraction, and with changing the porosity of the dust grains. And what they have shown that if the grains are two polars, like only 1% in the filling factor, then expected polarization fraction is too low to be detected. But if the filling factor is like around 10%, then the window of the polarization can be detected can become slightly bigger. So which means that we can detect polarization from wider range of the grain size. But basically, the single peaked behavior doesn't change. And these authors, Florian Kirchschläger and Giza Bertrand, calculated the polarization expected from non-spherical grains, but with the detailed calculations. And they have shown that probably, or not probably, if the grains are non-spherical, then the behavior at the large grains is slightly different. So even if we assume 1 millimeter grains, we expect to see some polarization even at the 0.9 millimeter. So obviously, these are one of the fields that we have to go. So please visit the talks by Ryota Zaki and Florian Kirchschläger. They are in this conference. Finally, I would like to mention the line polarization. As far as I know, the results are slightly discouraging. So, for example, the Vlemings et al. Reported a non-detection of the CN circular polarization from TW Hydra, and also the Ian Stevens reported kind of non-detection of the CO polarization from HD 142.527 and from IM loopy. But they have also showed that the tentative detection in the Stokes Q component. So, and also I found that Rachel Harrison is showing that another upper limit on the circular polarization of AS209, and also Lankar showing some more predictions for the line polarizations. So please check them out, their talks as well. Okay, now I came to the summary. So I have talked about the millimeter wave polarization in protoplanetary disks. And disks are showing the combination or superposition of self-scattering and alignment-induced polarization. I hope that you're convinced. And I also have discussed the grain size inconsistency. So many disks show the self-scattering induced polarization at 0.9 millimeter, which shows the 100 micron presence of the 100 micron size grains, but it's inconsistent with the spectral indices analysis. So that's why there are some ideas, for example, flat gas surface density or optically thick disks, optically thick substructures. I would like to emphasize that grain microphysics is really essential and needed. For example, porosity matters. Mu regime is very important field parameter space to discuss. And also, we really need a fundamental discussion on the alignment physics in protoplanetary disks, which is very missing. And finally, I discussed the line polarization. And so far, I think there's no robust detections. That's all from my talk. Thank you.
Thank you very much, Kataoka-san. I want to invite you to our university as a lecturer. It's a very good talk. Thank you. Okay, so we can go to the Q&A session, and I got many questions already. And actually, the most voted question is about the porosity topic. And you have already, showed us with one of your slides. But could you maybe, repeat, for example, what aspect is robust for the current interpretation, and what, aspects we have to be careful when we consider the porosity or the non-spherical grains?
All right. So first of all, for more details, please directly ask Ryota Zaki and also Florian Kirchschläger. And the general answer is here. So, as you see here, these are the filling factors. So for simplicity, we have always assumed spherical dust grains, which shows a very peaky function here. But also, we need this high number of high efficiency of the scattering index polarization to reproduce the observed polarizations. So for example, if you look at the green line, which is like factor of 10 lower than the compact dust grains, which is too low to reproduce polarization observed. So which means that grains are not highly porous, like filling factor of 0.01, which was my PhD thesis for whatever. But anyway, so polarization due to self-scattering says that grains are kind of compact. So I think that's the general conclusion. And also, I would like to mention that from the Giza-Bertrand paper, they have also shown that if the grains are porous, they also cannot emit the intrinsic polarization. So we saw self-scattering as well as the alignment in this polarization. And for the alignment in this polarization to be efficient, we also need the grains to be compact. So from both cases, we need the grains to be compact, roughly speaking. So these are the kind of general conclusion that I guess.
Thank you very much. We actually got the exact question. I mean, do you think current observations from ALMA support more compact growth than fluffy grain growth? So you have just answered that question too.
Oh, yes.
Okay,
yes.
Thank you very much. Okay, so go to the next most voted question. Okay, so the question is about the magnetic field orientation. So what if the magnetic field is vertical or not toroidal, I mean poloidal, near the midplane, for example?
All right. So yes, yeah, that's possible. And actually, we really don't know. And so, and as how to say, as I discussed in this talk, it's really difficult to distinguish the mechanisms. At least we can distinguish between alignment in this polarization and the scattering in this polarization by checking the wavelength dependency. So, but we have no tools to distinguish between the alignment with B fields or alignment with gas flow or alignment with radiation. We still we need very phenomenological discussions. So the question was, if, for example, if the magnetic fields are, for example, in the radial directions, then of course it can explain the azimuthal pattern polarizations, and which may be the case. And I really don't have the answer. Probably, if someone is successful on detecting the line polarization, then we can know, roughly speaking, for example, the strength of the magnetic fields. And if it's spatially resolved, then we can guess the direction of the magnetic fields, I think. So probably if the circular polarization is detected, then we can go to the next steps to really see the magnetic fields. That's what I think.
Okay. All right. Thank you very much. Then go to the next question about the 100 micron size as the maximum grain size. So how are you sure that 100 micron size is the maximum size? Because there should be a size distribution for dust grains, and maybe one observing wavelengths just picks up grains in a very narrow range. So how are you sure about the 100 micron?
Okay, what I can say is that we assume a very typical assumption, which is the power law size distributions with the maximum grain size. And the power law is always minus 3.5. And if this is the case, the opacity is dominated by the maximum grain size. So if the grain size dust grains have a power law size distributions, then I guess that the maximum grain size dominates. That's robust. But for example, if for example, grains have two populations, like very small grains and very large grains, or probably with planetesimals, then of course, I don't know. What I can say is that if you assume typical power law size distributions, then the Amax dominates the opacity. Yes, and also if the Amax is 1 millimeter, then it's really difficult to reproduce the polarization. That's what I can say now.
Okay, thank you. And I actually got the maybe similar, but not exactly the same question. So the question is that to what degree is the 100 micron value representative of the particle size and not of the size of the substructure in a much bigger aggregate particle?
So, okay. So I think that so he or she is thinking about a very large dust aggregates, and then
100 micron grain can be the substructure. I wouldn't say monomer, but yeah.
It's very speculative, but I think that basically albedo is the function of the largest scale of the dust grains. And of course, the polarization efficiency is very dependent on the shape that is shown by Florian as well. But for albedo, I think largest scale determines. If this is the case, then the largest size should be around 100 micron. So, which does not make the situation better, but we need 100 micron or maybe aggregates which has smaller Stokes numbers. But sorry, it's very speculative things, and I really don't have a clear answer for that.
Okay.
Yes, but yes. So that substructure of dust aggregates is one of the interesting questions. Thank you.
Right. Okay. Thank you very much. Then go to another aspect. So this is about alignment mechanism. So the question is that how does the collisional timescale compare to the various alignment timescales? So could collisions between the aggregates cause their random spins and alignments? Timescale of collisions and alignment mechanisms.
Collisions.
Which is dominant?
I think the collisions to the gas molecules is well. I mean, I think the question is about the collisions between dust grains.
That's right.
Okay, let's get back to the figure by Ryo Tazaki. Okay. Wait. It's also speculative, but I think the timescale of the collisions between dust grains is much longer than the timescales for considering the alignment, which has a much shorter timescales. And I forgot the details, but I think he assumed like 50 AUs in this case. So the timescales for alignment is like 4 or 5 orders of magnitude shorter than the Keplerian timescales, and I think which is much shorter than the collisions between dust grains. So, I think what is more important is the gas turbulence. So, if the gas is very turbulent, then they will randomize the direction of the alignment. So, which makes no alignment for the dust grains. So if this is the case, then we don't see any polarization due to alignment. So probably, which means that because we already observed many alignment in this polarization, probably the gas turbulence is very weak, as shown by Kevin and Richard Teague. Yeah.
Okay, great. Thank you very much. Then the next question is interesting. So a question from Kundam Kadam. So are there any observations of the evolution of the polarization maps, for example, across a few Orionis outbursts?
That sounds very fascinating, and I really would like to see that. And but unfortunately, answer is no. And probably because of the required observing time is very long. So the levels of the polarization fraction is only 1%, or in the case of H tau, it's only 0.5%. So to detect such a 0.5% of polarization, for example, let's say that 1%, and to detect 1% polarization, we need the signal to noise ratio to be like 300 sigma to detect polarization with 3 sigma, if it is 1%. So that's why we really need a long exposure time, like hours. So that's why it's really difficult for taking a survey of many disks for polarization, and also for the fainter targets at 300 AU, like Orions. So, but if the ALMA-TAC allows, then we can make such a nice polarization surveys that would be fantastic.
Okay, thank you. There is a similar question, but this is for lines. If you have looked at the possibility of line observations, I mean, the question is that what are the prospects to study polarization with lines in disks? Do we need more sensitivity?
I'm not the person to answer, but definitely we need sensitivity. Sorry. But even with the upper limit, we can discuss the levels of the magnetic fields. And for example, the magnetic fields constraint from the paper by Vlemings et al. Is very, very tight. It's much, I think it's lower than expected. So I don't know. Probably we have to assume that the Zeeman polarization mechanism is correct. But then, which means that the strength of magnetic fields may be much lower than expected. If this is the case, then I don't know. Yeah, probably if we have a much bit better sensitivities, then we maybe detect that, but no one knows. Yes.
Okay, yeah, this is quite new aspects. Okay, and go to the next question. We have 50 seconds. So going back to the interpretation of the data. So the question is that, does the wavelength independent polarization in some disks imply the absence of 100 micron grains, or just that self-scattering is less important than other mechanism?
Okay, so I think that at least that excludes the possibility that Amax is 100 micron. So if Amax is 100 micron, then we would have seen the polarization due to self-scattering. So, sorry,
So
yes, this is so.
Okay,
yeah,
so you say self-scattering is dominant. Okay.
Yeah, but for example, even if we don't detect scattering in this polarization with these bands, but for example, if the grain size is 10 micron or 1 millimeter or maybe 1 centimeters, then we don't expect scattering in this polarization. So at least we can exclude this parameter space, but that's all what I can say.
Okay, so I think time is up for now. So thank you very much, Akimasa, to answer many questions, and also thank you for your questions, participants. Participants, you can also, put comments, questions in the Slack channel, day 3, polarization, a magnetic field channel. So please go there. And also, right, okay, yes. Okay, and also I'd like to remind you that there are many, very nice contributed talks in the conference webpage. So during the break or anytime you can please go to the website and watch the contributed talks. Okay, so Akimasa, many thanks for your talk and also answer many questions. Thank you very much.
Thank you very much.
Okay, then we go to the break for around 30 minutes, and please come back to 3:30 for the general discussion session. Okay, so Alvaro, Enrique, back to you.
Yeah, thank you very much, Misato. Thank you very much to the speakers for this morning. Yes, Misato said we're going to go into the break now, and then in half an hour, we're going to start with the discussion. Here you have some of the panelists, and well, the moderators are going to be David Wilner and Evin Van Dishek. The topics that we'll cover are the topics for the review talks on Monday and Tuesday. The review talks of today will be in the discussion session on Friday. And here's the list of panelists. And now I'm going to share you, in a few seconds, I'm going to share you a poll, which is a question with which we're going to start the discussion in 30 minutes. So please stay tuned. See you soon. All right, looks like it's time. So it's a great pleasure to have this discussion today, and it's a great pleasure to have David Wilner and Evin van Dijk moderating it. So please, David, Evin, take the lead.
All right, thank you. Welcome to this first discussion session of the conference. And for the next hour and a half, we have the invited speakers from the first 2 days of this week. And we have a panel of 20 experts to delve deeper into the topics that have been reviewed so far. We've had a lot of great questions and answers following the invited talks, and many more of these have been addressed productively on the Slack channels, but I know that there are surely many more, so please continue to use Slido to submit and vote your questions. And now I'll pass over to Evin van Dijk to explain the organization of this session.
Yes, good afternoon, everybody. It's great to see so many of you online. I think we are now on 200 participants here, and probably more still through the YouTube channels. Fantastic to see so many of you around the world. I'm also very pleased with the high quality of the talks that we have heard so far, and of course the excellent recorded contributed talks that are basically posted. So please do go and listen to all those great contributed talks. It's a pity that we cannot highlight more of them here in this meeting. So this first discussion session is actually on a number of topics that were discussed in the first 2.5 days. It's on demographics, it's on disk evolution, on chemistry, on disk dispersion, debris disks, and exoplanets. And that is also the order in which we will take that. So we don't intend to jump from chemistry to exoplanets and to debris disks and back and forth, but we try to take them sort of in that order: demographics, disk evolution, chemistry, disk dispersion, debris disks, and exoplanets. We'll do it in that order, and then we basically can go back at the end with still some general questions. So it also means that there are a number of topics that and also questions that have been raised already that are more for the second session of this conference, second discussion meeting, and that's dust evolution, polarization, disk dynamics, young exoplanets and circumplanetary disks, disk multiplicities, class 1 disks, and substructures. So especially substructures is a topic that is actually for the second discussion session. So save your questions for that. Indeed, submit your questions through Slido. And panelists, please raise your hands if you want to answer a certain topic. So we were actually starting with a question on disk mass, because I mean, all of these topics that we are discussing here, a fundamental element of that is the disk mass. And if you don't have that, then talking about disk evolution, etc., becomes already a lot harder. And so what is the best disk mass tracer? So let's see, Annika, can everybody see your the outcome of the poll now?
Yeah, I think you should be seeing it in your screen, right?
Yeah, I see it. I don't know whether everybody is seeing it.
Yes, everybody is seeing it.
Yeah, everybody is seeing it. Good. So it's 114 people voting. HD appears to be the winner, and then CO, and that's isotopologs. Millimeter continuum, rather on the low side, and then also some others. So I would like to invite the panelists to comment on this, the outcome of this. Is this surprising? Do you would advocate other, and more strongly one of the other outcomes? Who wants to actually start a discussion on this?
I can say something.
Yeah.
No, I agree. The HD, I would say, in combination with other tracers, is a very good tracer of disk mass. However, I'm a little concerned to rely only on HD, especially because
I know that now there are issues with the, I mean, I'm not even sure that there is a better instrument now to get additional HD measurements. My understanding is the instrument on SOFIA is not going to be continued, right? Maybe you can comment on that.
And indeed, there is a big issue in the future observations of HD, both SOFIA, but also this SPICA mission being cancelled. So it means that we now have to wait a long time to do that. But of course, having an argument like this, that this is so important to measure this fundamental characteristic of disks is, of course, something that we should use as a community to push for for future far infrared missions. And I know that some of you on the line have been doing that. I think Ilse is online. Yes, Ilse wants to add to this. Yes.
Yeah, I would love to. I'm optimistic. I'm excited to see the results, and I would love to hear what other what people who selected other were intending, and maybe they could add that to the Slack Day 3 general discussion thread. But I do want to also bring up that none of these are perfect. HD, of course, is that the line itself has a high upper state energy, and so it's tracing more of the warm gas, and so it still requires some information about the temperature structure to really determine what's going on underneath. And there's actually a nice paper by Jenny Callahan that's coming out soon on this topic for TW Hydra and reinterpreting the HD mass. So none of these are perfect. It's ideal that we would probably get all or more than one of these to fully interpret it. But like Ilaria said, we don't have a great, there's not a solid future right now for future HD observations, and we don't have that many detections. So as a community, what is our plan? Sorry, go ahead.
Yeah, no, I was just saying, I mean, you mentioned indeed the temperature structure. I mean, to what is our feeling for the accuracy of with which we can derive now the gas masses, so which is the total disk mass. So Ilse, can you elaborate still a little bit on that?
Oh, of course. I want to make sure there's we can speak across the panel, but I think that I'm excited to see with all these multi-line analyses that out there right now that, temperatures are able to be retrieved for the very commonly observed, frequently observed disks. But what about the little ones that Anna showed earlier, the compact sources, the ones where we know very little? I think that, I don't know. And I think there's a lot of work that could be done on how well can we measure temperature of an unknown disk, unknown star system. So
Right. So Lukasz wants to add to this. Go ahead, Lukasz.
Yes. Thanks, first of all, for also to finish this, because I want us to shift the topic a bit to the continuum part, because the gas is, of course, very important. But I understand the question was the best disk mass tracer as what is the most important one. And I do wonder whether the focus on we've given all the uncertainties, especially gas to dust ratio, doesn't the dust provide us with the most important constraint, for example, for the planet formation, because that's from what you need to start building your cores, and especially for the gas giants. And of course, then the gas is also important because that sets up the composition of your atmosphere. And but I think from the point of view of starting the planet formation, actually we need to address the dust disk mass, and then the millimeter continuum will be indispensable.
Yeah, so let me follow up on that because that also touches on yesterday's discussion where there may have been some confusion according to the chat. Well, first of all, given also the talk that we just heard, to what extent can we still be underestimating the dust masses? And then the point that you brought up in terms of the planet formation efficiency that we would need in order to explain the exoplanet cores. Who wants to say still a few more words on the millimeter use of the millimeter continuum?
Yeah, I want to add that, I mean, I completely agree with you, Lucas. I think actually the millimeter continuum is very important to learn about planet formation, but the evolution of the gas may be different. So I think we really need to get an independent measurement of the total disk mass, which is most likely early on in the gas. Yes. And on the previous point, I think, I mean, my opinion is that we should put a bit more effort on the CO and its isotopologues to figure out if we can learn a bit more about, I mean, if we can have a more robust measurement of the disk masses, because as I pointed out yesterday, and maybe some people here can add to that, because it's really not my field, but there are some discrepancies out there. So the picture is not yet clear, and I think we need to dig into it a bit more. That's my opinion.
Yes, well, I wanted indeed to come back to the CO and its isotopologues. It's a pity that one of our panel member, Keizang Kokuzang, is not yet online, but let me then, Anna is there also. Because there are actually some disks where CO is detected, even the isotopologues 13C, 17O, implying actually very high gas masses, including HD 163296 disk. So there are certainly cases where CO can be actually a good tracer, and that's, I think, especially the warmer disk where less of this chemical transformation has taken place. Anybody who wants to comment on that? Yeah, Anna, go ahead.
Yes, I wanted to make a similar comment indeed, because what we seem to find is that as soon as you go to slightly warmer disks, then the CO is still it is still there. I mean, you see bright lines. You see even the isotopologues, the very faint ones, and actually an interesting paper was the one by Mikkel Kama and collaborators this year, where they used the Herschel data on some of these disks to get some lower limit to the disk mass from HD. And you could see that it was in principle, in some cases, compatible with the CO detection. So I think there is a difference between, let's say, Herbig-like disks and fainter, colder disk. Yeah.
Mm-hmm. Yeah, very good. Somebody nominated Megan actually to jump in on this topic. Megan, you have anything to add to this?
Hold on, let me turn on my camera. Yeah, I mean, I guess I'll defend the millimeter continuum a little bit. I think, you know, in trying to define what the word best means, if best means, you know, the most accessible, then millimeter continuum becomes important. And I think the best way will be some sort of combination of all of these, right? Because as people have already pointed out, there are issues with all of them. And if we can somehow, you know, get measurements like this for a larger number of disks and start working out the issues. And then maybe I've asked people before for some sort of calibration for the millimeter continuum so that we can get these measurements for a lot of disks through this more accessible method, and then have some sort of correction, right, that we can apply to make it more accurate.
Yeah. Giovanni has also a comment on this. Thank you, Megan.
Yeah, so just a quick comment about the calibration that Megas was mentioning is that it's always very puzzling to me when I look at the few detections of HD that actually they are consistent with the mass derived by the continuum. And theoretically, I can think of many reasons why this should not be the case, because we should be losing a lot of dust on the star due to radial drift. Yet, it's only 3 cases, so the statistics is very poor, but yet in those 3 cases, if we multiply the dust mass by 100, we get the gas mass inferred by HD. And to me, it's really a big puzzle.
Exactly. I was just going to ask how many sources do we have evidence that the gas to dust ratio is not 100? Because that is also very interesting. Now, all of a sudden, I see a lot of hands. We need to wrap up this particular topic within the next 5 minutes. So let's see. James, Uma, go ahead. First James and then Uma.
Thanks. So Elfa asked who voted for other. I didn't vote for other, but I want to raise a point that is useful to not forget the constraint that the accretion rate provides.
Mm-hmm.
Given an accretion rate and an age, If you believe it's a truly viscous disk, then you can get the mass out. But if it's not a viscous disk, it still provides a constraint as to what the disk mass must be to provide that accretion rate. And I know many of the CO masses fall below that constraint, which is also puzzling.
Yeah, exactly. So, but they are not too far from dust times 100.
Yes.
For reasonable ages. That's yeah. Uma wants to jump in as well.
Hi, can you hear me?
Yeah, go ahead.
Okay, sorry, I can't get my video to launch. But yeah, so I wanted to jump in on Giovanni's comment about the gas to dust ratio. This is something that's been puzzling me as well, because I also noticed that the gas to dust ratio was 100, which is very curious to me. And we have a paper coming out hopefully soon enough that sort of re-examines the CO and continuum, and actually we find that if you sort of look at what the gas to dust ratio is implied, it does sort of seem to imply that it stays close to 100, maybe not orders of magnitude off. I think that's very curious. So this is applied to lupus, of course. And I think the other thing that I would like to also point out is that if you really want to understand about planet formation, sort of looking at the dust mass or looking at disk mass, dust versus gas, I think that's more interesting relative to how they evolve, because like I think it was Laia who said that you expect them to evolve in different fashions, because the solids are presumably going into some sort of planet formation process, and the gas mass is being removed. And I think if you really want to understand about how does the environment change, and how does the gas, for example, affect or influence all the planet formation processes, you really want independent traces of both. And I think that from the point of view of disk evolution, I would be more interested in how gas is evolving relative to dust. And to that extent, I think given that HD and CO, HD because of the temperature issue that Ilse pointed out, and CO because of all the chemical issues, as we're computing those, and we actually find that that it really is.
Yeah. Yeah.
It's kind of similar in terms of the total mass of the disk they trace, which is very little. Actually, it turns out that the mass of the HD is tracing, if you compare, from models.
Yeah. So Omar, thanks very much. Thanks very much. We look forward to your upcoming paper on this. That will be very interesting. I remember Dave Hollenbach also showing some back of the envelope calculations on how gas to dust ratio should change as a function of age. So it's very good that you're revisiting that. I'm wondering whether we could get the poll actually removed so that we can actually see all the participants. That would actually be nice. And let's get sort of the view of all the participants. Okay, good. So actually, so that we can go in that. Anybody else still something on a comment to contribute actually on disk demographics? Silence. If not, then I suggest we can, of course, continue to have questions on this, but then I suggest that for the moment we move on to the next related topic, of course, which is disk evolution. David, go ahead.
All right, so if we can, in fact, establish the properties of disks, and in particular as a function of age, which is pretty tricky for these young objects, then we can start to say something about disk evolution. One of the most popular questions on Slido here is, are disks evolving viscously? We know that the disks we observe are accretion disks, but I think it's fair to say we don't fully understand the physics of accretion and what we really mean by viscous accretion. So I want to throw that question to the panelists and see what they have to say. Looking for hands. Barbara?
I'll unmute myself first. No, I obviously don't have an answer to that. I don't believe any of us have that. But I would like to add to that question that maybe we need to basically take a step back and ask, what are the really diagnostic of a population of disks that is evolving viscously? What should we be looking for? So I know that Giovanni Gozzotti and other people have also looked at various ways of, for example, detecting the expansion of the disk. There is one solid and robust prediction of a viscously evolving disk. I would say, I hope, Giovanni, I'm not offending you, but with limited success so far to really have let's say, a clear answer to that. And so there's a lot that's going on. Opacities play a role. Giovanni always shows the opacity cliff, the white cliffs of Dover. Maybe you can explain that. But maybe there's something else that we can look at when we look at populations looking for viscously evolving disks. I think if we just look at accretion rates and single disks, particular disks, we can't really say much, because viscosity is something that what we care about viscous evolution is because we care about the surface density evolution of the disks, which is basically what goes into our planet formation models. And so I don't think we should be caring about a single object and deciding whether that's now MRI active or not. We should be just looking at large population and looking at what are the diagnostics that we can infer from a population of disks that is evolving viscously. And there's lots of work as well by Giuseppe Lodato on that, looking at demographics and populations, and also work in the group of Ilaria Pascucci. So maybe we can change the question a little bit so that those of you guys who have worked so much on that could maybe say something.
Right. Well, of course, what we want to understand is the angular momentum transport in the disk, but angular momentum itself is not easily observable. So let me throw that to Giovanni, and he can address your comment.
Well, yeah, I mean, of course, this is, a big question, how do disks evolve? But I completely agree with what Barbara was saying. And I agree that the approach should be the one of looking at large population of disks, because that's really where we can see how the different mechanisms of angular momentum evolution leave their imprint on the way the disks evolve. And yeah, if we look at the most fundamental difference between viscosity, so angular momentum redistribution, versus wind, angular momentum extraction, then really the difference is in the evolution of the size of the disk, because it's inescapable in the viscous evolution that the disk must expand and become bigger. And I would say that, speaking as a theorist, the biggest problem I have is really the lack of observations, because we have very few disks at a population level, so in terms of demographics, where we know the disk sizes for large samples of disks. And in most cases, we know it only for the most massive disks. So as a theorist, that's at the moment my main limitation. Clearly we have to do some modeling, and it's not that we can just take the number that comes out of the observations. We have to do some processing. But from the theory side, I think we know how to do this. The biggest limitation is that we don't have the data at the moment.
Let me inject.
And if I may add to what Giovanni said, it's probably obvious to everybody, but we need the gas disk size.
Yeah. Thanks.
Let me inject an observer's question here. What do you actually mean by disk size? What is it that you need to measure?
Yeah, I mean, we can get into the detail of how we do this, but I think to some extent is, the alpha light radius or whatever other fraction you want to define of the flux of a tracer of the gas density. Yeah, that's what we need to do. That's what we need.
Coco?
Yeah, thanks. I definitely agree. So it's very important to get a population of disk sizes, especially the gas disk size. So one thinking I have is from the latest MAPS result is with a high resolution observation, we were able to trace the CO column density profile between like 100 to 400 AUs. So it seems very interesting shallowly decreasing tails. I'm wondering like if we can do, of course it will be a much limited sample. So increasing the sample of the surface density profile, of course, still will be affected by, say, photodissociation and other mechanisms. But this also gives us some hint about how some relative constraint about the mass distribution in the outer disk. So that also offers additional constraint besides the disk sizes to maybe how the mass is distributed in some constraint. So I just wanted to say, with spatial resolution, we are approaching some detailed constraint for a few individual disks. And that could be another way to explain this constraint.
Yes. Shoning, I see you have your hand up.
Yes. So I think, yeah, I just sort of follow up from Coco. I think this is really a fundamental problem. And I think just like the disk mass problem, no method is perfect. All suffer from various deficiencies. And so I think we really need to tackle this from multiple angles. So from theoretical point of view, yeah, we have done many different kinds of simulations to try to address the mechanism of angular momentum transport. There are pure hydrodynamic instabilities, which give you some level of alpha, and that seems not quite enough to account for the observed accretion rate. And so it seems like the wind-driven accretion is essential, but that doesn't exclude the presence of additional contributions from turbulence. So it might be that just there's a mixture of both turbulent-driven and wind-driven angular momentum transport, and so you can have both certain level of turbulence in the disks, as well as you have large-scale MHD wind that drives disk evolution. And it can be that the wind dominates, but turbulence still contributes. And the other thing is, I think from observational point of view, people also talk about, say, external photoevaporation, right? So even you have a, say, wind-driven, MHD wind-driven disk, which you might expect that the disk should overall shrink with time. But if you also have a evaporative outflow, that will also mimic, right? So that will make the gas in the same time more extended. So it's unclear what the signature of that is. And I think another angle is just the measurement of turbulence, which was mentioned today, in today's talks. And I think there's some kind of, if the level of turbulence is really as what people have measured, most of the disks are very weakly turbulent. It's going to be hard to reconcile with the fact that the disk is going to be viscously expanding. So I think really we need to combine multiple pieces of constraints to this problem.
Yeah, thanks, Shoning. This is a great fundamental question, because I do agree it's multifaceted, and unfortunately I don't think we're going to solve it today. But I'll throw it to James Owen for maybe a final comment on this issue.
I was just about to turn around Shuning's comment back on him and ask him a question. So in the case of external photoevaporation, it's right, it will make the disk shrink, but it will make the disk shrink till it reaches an equilibrium where the external photoevaporation rate equals the rate at which viscous spreading is feeding it outwards. So do you think there's any mileage in working out how an MHD-driven wind-dominated accretion may evolve under the influence of external photoevaporation? And then we can compare sizes of disks as a function of UV environment as a possible diagnostic test.
You can go ahead, Juning.
I don't think there has been any work done on this front, and so I don't know the answer. But I think it's something very useful to consider.
I think there has been work done on the disk masses in the different environment. I mean, in external photoevaporative regions, like, you know, in the Orion close to the trapezium, for example, or the Sigma Orionis cluster, to come back to Megan's work. I would like to hear a little bit more still, maybe about sort of this relative importance that people see of disk winds and photoevaporation. That's also one of the questions I think that comes up in the Slido.
Ilse?
I would just like to hear a little bit more about predictions for small dust grains in winds and basically observable diagnostics of winds. I know there are a lot of efforts to look for gas tracers of winds, but it's really difficult when you're looking against the very bright Keplerian bulk motion of the disk to find small deviations to see large scale winds. I'm not talking about things, you know, launching very close from the star, but the larger scale structures. And now that we're going to go in, you know, we have some initial beautiful images from the DART survey of scattered light images of disks, and likely, hopefully more with JWST. You know, are there predictions for how we might see the imprint of winds and transport on the small dust grain population? And could someone speak to that?
That's a hard problem. Barbara, I see you have your hand up.
So we started doing that with our simulations for X-ray photo operation, and also did some tests with a very simple MHD disk. So the first paper is out by my student, Raphael Kranz, who basically shows how we expect different grains to be lifted at different heights above the disk and at different radii. So there are very specific shapes. There's also now old work by James Owen in 2012, and there's work done on MHD winds in particular, now I forget, by the Japanese group. So there are predictions there. Now Raphael has also, well, the paper is now submitted, produced diagnostics for sphere observations, what we should see. And we have been in contact also with Antonio, maybe you can mention what we've been talking about, to see whether we already see maybe some of those in the many images that we already have. At the moment, we're inconclusive, and so I know that the observers are now re-reducing and re-looking at all the data, trying to please us, but I don't know exactly where we're at now. So maybe also an observer could comment. So to say that we are calculating, and we have calculated and put out the diagnostics for the dust, this is a very interesting question.
Well, there are certainly a lot of very subtle features in the scattered light images that are difficult to explain. Is there someone who would like to address that in particular?
Sebastian had his hand up already for some time. Maybe, and indeed Antonio Garoffi could also address that.
Okay, Seba?
Yeah, I just wanted to kind of mention the recent work by Josh Lovell, where basically it's related to what we're talking about, winds and observational constraints. So this is a class 3 disk in Lupus, so 2 to 3 mega years old, with dust, very little dust. We don't know if it's just leftover dust or replenished by planetesimal grinding. And we found gas, and this gas is really fastly moving outwards, we think. It could also be inwards, but we think that the preferred scenario is outwards. But this is much faster than like a photoevaporative wind. And we think it could be an MHD wind, but we really need like modelers, theorists to come up with a model that could explain that. And this is just at the time where we're all thinking disk could be dispersing. This is just like a good snapshot of a disk that could be like in that moment we're interested in. Josh has a talk, I think, if you haven't had a look at it, in the debris disk section, but it's really relevant for disk evolution, I think.
Right. Well, certainly observations in that phase are very valuable because maybe some processes are happening quite quickly. So yeah, Antonio, maybe you could say a few words about the scattered light.
Yeah, so the question is, well, that's an observer question. How many small dust grains do we really need to see this wind? Maybe in comparison with something we know. Like, for example, we know that we always see a bunch of photons from the cavities of transition disks. That is more or less always the case. So maybe with Barbara, we should discuss in comparison with maybe the most depleted transition disk that we know in terms of gas, and we can assume that small dust grains that will have the same amount of depletion as the gas in principle. Then if the number we expect from the transition from the cavity of the disk is comparable somehow to what we expect from winds, because then it totally makes sense that we would see these small dust grains in the wind somehow.
Asuncion, you've had your hand up for a bit. Thanks for your patience.
Yes, I have a question for Barbara or anyone. What about PAHs? Do you expect to detect the photoevaporative winds in the near-infrared bands?
Sorry, I didn't quite catch that. What about the what?
PAHs.
The PAHs? Well, PAHs is a good question. So some of you will know that I'm not a believer of PAHs in Titori disks, because we don't actually see PAHs in Titori disks. Maybe Uma can say something else, because she probably thinks the PAHs are there. So that's a good discussion. But I am not aware of many detections of PAHs in Titori disks. Of course, this is different from if you look at Herbig stars. There's lots of detections of PAHs. One possibility of why the PAH is undetected in Titori disks, since they should be detected according to models, is that they are actually destructed by the strong X-ray flux that comes in the surface layers of the disk, which basically means that the PAHs would also not be available to be lifted into the wind. So the wind can only entrain grains that are at the surface, at the base of the wind. If PAHs are destroyed there, then they're also not going to be in the wind. So I don't think that...
Yeah, if I may just interject here. So, I mean, it's also whether there's enough UV available to excite them. So this was also addressed in some, I think once you get below, say, K5, then you don't have enough UV anymore to excite them enough so that you see them in the line to continuum ratio. I should say that some of the transition disks have, of course, very strong PAHs, even if they are around low mass stars. And that's simply because you have more contrast, and the UV now gets absorbed by the PAHs rather than by the dust grains. So they are there. It's makes sense for that.
In the case of Herbig A star that you have PAHs, is it possible to detect photoevaporative winds with the PAHs in these cases of the Herbig stars when you have enough UV radiation?
So I guess what you mean is whether you would see the PAH feature being blue shifted, or is that what you mean?
You cannot see this, the velocity in the PAH.
No.
You would have to distinguish it from a background nebula, so that's not that easy.
If you have an edge on disk, then you can have some kind of atmosphere, no?
Yeah.
All
Maybe we
right.
need to move. Yeah, to move.
I was gonna say, Ari,
Can I add something to answer actually the question? So you asked also if there are signatures at near-infrared wavelengths of winds, and I have to say yes, and there are very interesting now with JWST. So some people might remember the excellent work by Tracy Beck and Agra Amboage using near-infrared AO ground-based in the H2 vibrational transition, and seeing this beautiful extended H2 on top of the scatter light images. Now, Ganji et al. 2020 have shown that many of the H2 vibrational lines are actually blue shifted. So I think this is an extremely good diagnostic of extended winds, and I look forward to JWST. That's it.
Okay. Fantastic.
That's an excellent point.
So I think just in the interest of time, we need to move on to the next topic, but if we have more time at the end, we'll return to disk evolution, which is clearly something that an area where we still have very much to learn. So I'll send it back to Aveen.
Right, because the next topic is actually chemistry, and I know we actually have quite a number of astrochemists in the panel. So Anna has summarized a lot of the observations of molecules in class 2 disks, but one of the questions that has also come up on the Slido quite a lot is how about the earlier stages, class 1 and class 0. Now, strictly speaking, class 1 and the earlier stages are for the second discussion, but I think for chemistry we can spend a few minutes in discussing this here in this panel, because I think we have the chemistry experts actually on this panel. So who wants to say something about chemistry in class 0 and 1 versus class 2 disks? Yes, maybe Linda, you can start with it, and then Coco.
Yes, hi to everybody. So yes, that's true what Ewin is saying, that there will be an invited talk tomorrow, I think, or the last days about class 0 and 1 disk, but I think it will be mainly about the dust. So maybe if we want to speak about chemistry, we had a nice review by Anna Miotello, but I think now there are lots of efforts to also characterize the chemistry of class 0 and 1. And this is for me, is very important because, I mean, one of the main breakthroughs that we are discussing in this day of ALMA is that the fact that we have seen these substructure rings and gaps in very young disk is actually pointing to the fact that planets formation starts earlier than we previously thought. So because of this reason, it's really important to characterize the chemistry of the disk at a younger stage where planets are forming. And I think also our view of hot Corinos is changing, in the sense that what before we called hot Corino, now that we have resolution with ALMA, we are starting to see the disk around class 0 and 1. And we, in some cases, I mean, still a few cases, we really see that we can detect in this disk complex organic molecules that directly arise from the rotating disk. I'm thinking about the work of Cinfelli, for example, but also the recent work of Eleonora Bianchi in Faust, and the paper of Maria Jose Moreira on the famous WLA 16293. And so there are okay, the work of Sakai on L1527. So I mean, we start to see complex.
Yes, indeed. So I think the message is class 1 and class 0 disks especially are much warmer, and so it's actually much easier to see all these molecules there than in the later stages when it's cold and it's basically frozen out. Coco, you want to add to that?
Yeah, so I think Linda already mentioned most of the important stuff. So I just wanted to say we do see like some evolution, at least for class 1, younger class 1 or class 1, class 2 borderline objects. They seem to have a higher CO abundance compared to many of the class 2 objects. So it's suggesting there may be some quick evolution at the 1 million year time scale. So I think it would be really interesting to look at, to have a systematic measure of a couple of the most important tracers to see what's the general trend for different molecules.
Yes,
all right. Ilse, you're next, and then Lukasz.
I want to also go along with Linda's point as well. In these earlier stages where there are detections of organics, and in some sense it's easier, as Avina said, than even the Titari stage later. But one incredible feature of these new observations is seeing the dust growth and the ring structure formation happening early on. However, on the negative side, that's implying this dust growth is increasing the optical depth in these earlier phases. And I want to caution folks from over interpreting structure in the chemistry in the earlier phases, be very careful with continuum opacity because it can really block our view of the molecular emission from these very warm regions. I also want to, since we're on the topic of chemistry, I want to ask, the isotopic experts here, sort of one of the features in which we try to connect the multiple stages from class 0, 1 to 2 is in talking about what is the inheritance or reprocessing as traced by the isotopic or isotope logs of the common molecules we observe. And so I'd love to hear a little bit more about isotopes and the status there, maybe Vivi or someone else on the panel here.
Good point. Let's first still finish this particular discussion, then we'll come to the isotope logs. Lukas, you had wanted to add to this as well.
Yes, I think it's in a sense related because, I mean, as much as isotopes in general, the question is what happens across the evolution, right, with the chemistry. And it's just because we see them so much chemistry in class 0 and 1, basically because they are warmer. But the key question, and we probably expect that all of this is frozen out in class 2, but the key question is what kind of evolution those molecular species undergo, starting from 0 and 1, and then go to class 2. Because, I mean, the relevant point is, can we use this complexity that we see in class 0 and 1 and the power we have now with ALMA to observe this in detail to actually predict what happens to that later on and what kind of composition is in the plant growing material. And this is both related to the fact that if we start early the formation of planetesimals and we inherit the composition of class 0 and 1 disks, the ice lines are shifted in different direction, a bit further away because of high temperatures, and this also modifies how what is the conditions at the current formation of site of plant formation.
Yes, I mean, I think it's indeed an important question simply because we don't see the complex molecules, or much more difficult to see them in the later phases. Doesn't mean that they are there. They are simply locked up already in ices or otherwise, and they're just making invisible. In fact, Eleonora, you may want to add to that as well.
Yes, thanks. I would like to come back also on the opacity point pointed out by Hill. So there is a new paper of IRAS-4A with VLA observation actually, and these show that exactly the methanol is detected also in the protostar of the binary system that was not detected in the millimeter as a not Corino. So this point out that the opacity can be a problem in these early stages.
Yes, absolutely. Yeah, absolutely. I mean, that's a beautiful example where you see sort of at the longer wavelengths, you see the molecule popping up again and on sort of 20 AU scales.
So going into this longer wavelength can be useful to overcome this problem. And also for the chemical complexity from class 0 to the class 1, where we observe the complex organic molecules, actually, there are not so many sources in class 1, but in these few cases, we see that the molecular abundances ratio is not so different from the class 1 stage. So it seems to be a sort of continuity in the chemical complexity.
Yeah. Well, and also even with the pre-stellar stage, that's of course also a very interesting stage to compare with that. Yeah, I would try to touch on Ilse's question about the isotopolog. So how about deuterium? Because that is one of the easiest ones to observe in various molecules. Deuterated formaldehyde, deuterated methanol, etc. Do we see evolution in that?
I'm sorry, I didn't raise my hand. The deuterated formaldehyde, as far as I know, has it been detected? Can't recall one off the top of my head. I don't see any nods or shaking. But please in the Slack chat if you have an example. But in terms of the other deuterated smaller species, the challenge is you can see the more deuterated complex organics in the earlier phases, and it's a challenge just to see methanol, deuterated methanol, or methanol period in T-Tauri disks. And so we're relying on extrapolating from the smaller species. But Karnoberg has a nice paper out just recently on very high resolution observations of DCN and DCO+. And we do see evidence that there is active deuterium fractionation occurring in the upper layers of the TW Hydra disk. Statistically, that's one disk. We can't extrapolate everything from TW Hydra, but it's at least, we're seeing active deuteration. This is again the surface though, and in terms of what's going on in the midplane, the picture is much less clear. And so the chemistry of the midplane seems to be a bit less active and maybe closer to the inheritance picture, though hopefully we'll have more direct constraints on this with JWST observations of midplane ices, etc.
Yes, I was just going to add to that. So can somebody speak to that? What's JWST going to bring us in terms of disk chemistry? Who wants to add to that? You mentioned already ISIS. That's sort of one of the science cases, indeed. Yeah.
I mean, I could keep speaking a little bit. I mean, JWST will be, it's very kind of interesting. And I feel like Ilaria should also speak to this as well. We'll have a lot of constraints about the very, hot regions and close to the star in the gas phase. We'll have a lot of, or hopefully a lot, and we'll have constraints on the outer disk icy reservoir as well. It's not the intermediate chemistry. Hopefully, maybe those missing pause that Barbara is talking about, maybe if we have really deep observations, maybe some pause will be seen too. But in terms of just what JWST can do, it serves this dichotomy of the really hot stuff and the very cold stuff. I mean, Ilaria, you could also.
I
can.
We get already to the inner disk chemistry, indeed.
So I think there was a paper recently by Andrea Banzatti in collaboration with me and many others, trying to make that connection of the outer disk, the dust disk radius and the inner chemistry, because there is potentially one could potentially detect pebble drift this way. And with JWST, it would be obviously, the tracer would be even more obvious, because then you can access those optically thin lines in water lines, and then you can better estimate the column density of the water in the inner disk. So I think that's potentially a very interesting direction. Plus, JWST will enable us to get to the chemistry, the inner chemistry of very low mass stars and dwarfs, which were almost inaccessible with Spitzer. So I think that's also an interesting direction.
Just to make sure that the audience understands, this is simple molecules. Now we're talking about HCN, water, C2H2, etc. We're not talking about the complex molecules. That's
almost no chemistry.
Sort of the domain of the earlier stages in order to detect them. That also starts to relate to the dust traps. I'll be coming back, maybe do that a little bit later when we also start to make the connection with exoplanets formation. In the remaining few minutes of this discussion on chemistry, I want to touch on one of the questions that came up, and that's basically the small disks. What do we really know about the chemistry of small disks? Because we know that the bulk of the disks are actually small. If you look at the disk demographics, outer disk radii somewhere between 50 and 100 AU, rather than the gigantic disks that we have seen where most of the chemistry studies are. How much do we really know about these small disks? Yeah, Anna?
Yeah, so then if I'm wrong, please correct me, but I would say we basically don't know anything. So I mean, if you really mean the very small ones, they are also very faint, so they haven't been the first choice for the, say, gas ALMA proposal. So we don't know almost anything. Even the CO observations are really rare because they are shallow, so they come from the survey. and many of these disks are not even detected in 12CO. So we really low a little bit. There have been some efforts to look at binary disks with ALMA, in particular in towers. And there so these data are not out yet. Hopefully a publication will be out soon. And here we have, there are deeper observations of CO and of some other molecules. For example, I showed yesterday in a paper that we detect formaldehyde in a couple of these disks, even though these are still so in the binary system that we look at, usually is the larger disk that is showing the formaldehyde. So in a way, it's not that small. So I'm talking about binary disks because we know that we expect them to be small. But I think this is definitely a place where we don't know much, but I don't know if anyone else wants to follow up on that.
Coco, yeah?
I remember in July, Karen and her student present some result about chemistry in M-dwarf disks. I think those are selected from Lupus and Taurus. So those are small disks, M5, M4. So they have quite some detection of molecular emission. So I think that's a good start to help us understand some chemistry features in small disks. I also wondering about this sort of, so with JWST sensitivity, so we also can move to the lower disk mass ranging and also the more involved disk range. So can we use some of the combination of the samples to move to the smaller disk chemistry with the innermost region and the outer disk with ALMA?
Yes, the innermost disk region will not care so much about the outer the outer part of that. Yes, I see that Linda wants to add to this discussion as well. Go ahead, Linda.
Yes, concerning small disk, I wanted to say that in the ALMA.chemical survey, we have a couple of Taurus disks that are also quite small, about 70 AU radius. They are Digitau and Auro 613, and we see quite bright molecular emission, for example, from H2CO and CS. And of course, what we found in general in this disk, because these are a bit at the transition between class 1 and class 2, I mean, are a bit earlier, so probably they are more massive, and we see higher column density with respect to, I don't know, the typical class 2 disks. So, but these are small, they are very compact, more less than 100 AU, but still bright in molecular emission.
All right, good. This has already been a good discussion about chemistry. Anybody else who wants to add something on this topic or wants to bring up something about chemistry that we haven't touched on yet? Ilse.
I would like to also bring in the folks working on the later phases, the class 3 debris disks, and we have these gas observations that we heard about nicely from Meredith. You know, Luca has done some studies on looking for molecules beyond carbon, looking for things beyond oxygen. I guess this is, we don't need to end the story at class 2. We can start to
in fact, usually we end the story at comets. That's if you look at the fantastic results on the molecules in comets, 67P is a wonderful comparison at the late stages to look at the chemical composition. But actually, that brings us right into the debris disk stage. So maybe we should have one or two people answering this question, and then we slide basically into the debris disk discussion. Anybody still wants, Seba, you want to still add on the molecules in debris disks? No.
Yeah, just to answer or just to provide some thoughts about what Ilse was saying. So yes, at the moment, we're not sure basically if the gas we observe in debris disks is secondary and produced by basically outgassing from planetesimals as they break down. We don't know if that means that there will always be gas for 100 or 500 mega years around a planetary system, but there will be a period in which the gas densities drop, or they are constant, but the hydrogen density, the hydrogen abundance just goes from basically 1 to 0, and how quickly that happens as CO is being replenished Like those are things we don't know, we're starting to explore. Something we have very little idea is if there would be any kind of chemistry, would there be any molecule formation in this period? We know that CO gets photoassociated and all the other molecules get photoassociated very quickly. Basically,
yeah, now photodissociation lifetimes are short, although the point about the carbon shielding is very relevant, but that works mostly for CO, not so much for the other molecules. Okay, yeah, no, these are very good points. When does the hydrogen disappear versus when do the molecules disappear? So that's a very valid point. David, over to you.
All right, so that's a good segue into sort of further discussion of disk dispersal and debris disks in particular. There are a number of provocative questions on this topic. One that has been voted up that I especially like is perhaps more a nomenclature question than anything. But are all circumstellar disks debris disks? Does any of the panelists want to attack that question? Seba, why don't you go ahead and get us started on that?
So I thought about the question. I think what's behind is if there is always dust collisions and fragmentation going on in both disks, which one is a debris disk? And the way I would personally define it in a theoretical way is in a protoplanetary disk, let's say, the mass is moving from small grains to larger things, while in a debris disk, the mass is moving from large things down to smaller things. So kind of where the mass flux basically is the way I would define it.
All right, that's one way to think about it. Let's see, we'll go to Mark Wyatt next and then Meredith McGregor. Mark.
Yeah, I guess that there's a debris aspect of collisional destruction in protoplanetary disks. So, but there's also grain growth. So the models of protoplanetary disks involve dust growing and then fragmenting. So in that sense, there is a debris disk aspect. But maybe the important question for debris disks is whether there are planetesimals, and if there are planetesimals, whether they're being destroyed and broken up. And that's what we don't know in a protoplanetary disk. We know in a debris disk there must be planetesimals and they're colliding and getting destroyed. In a protoplanetary disk, we don't know. There's some missing mass, so maybe the missing mass is in planetesimals, and if they're in planetesimals, if they're colliding, they're going to be getting destroyed and breaking up and replenishing some of the dust that's in a protoplanetary disk, but we don't know to what extent.
Right, that points to the question of when do planetesimals form and how do they form and how quickly, and that's probably a topic for the discussion session at the end of the week after a number of more talks. Meredith, did you want to say a few words?
Yeah, I was just looking through the questions on Slido, and there's a sort of related point saying, whether we're tying ourselves in knots by trying to define all these different classes specifically. And I just wanted to raise the point of a question that I've gotten asked a bunch at different conferences that are maybe more outside of the disk community on how well we actually know the ages of systems and then use that to define categories of different types of disks and disk evolution, which I think is an interesting thing to keep in mind, right? In that some of these objects are in these moving groups where we have a pretty good handle on age, but there's a lot of sources that we don't have a good handle on age. And we as disk scientists use that a lot to define this evolutionary sequence. And, there's some possibility we could be wrong. So how do we define classes and evolution of planet formation when we don't have a good handle on that?
Yes, well, there's a continuum of evolution, and it may in fact overlap depending on which individual system one is looking at. And there's a related question on Slido that I know there's some recent work on, so I'll pose it. Is a sensitive survey of class 3 objects needed to understand the dispersal of protoplanetary disks and the emergence of debris disks? So that has at least 3 different pieces of jargon embedded in the question about evolution. Looking for hands. Mark Wyatt.
Well, I guess seeing as I'm involved in one of the studies that that did this, looking at a deep observation of class 3 stars, I think it should be done. Yeah, it's important to understand the evolution. Yeah, because otherwise we're just assuming that they're diskless, whereas actually we're finding that 20%, so 1 in 5 of the class 3 stars do have disks around them, or they still have circumstellar emission. So
at what age, Mark?
Well, that's at 2 million years. So that's in lupus.
Okay.
But that's a region where most of the stars are still protoplanetary disks. So whatever is in the class 3 stage is presumably has just lost its protoplanetary disk. It's one of the earliest systems to have lost it. I mean, you said there's some different nomenclature in there that is good to unpack. I mean, the class 3 stars are just defined by having a lack of 24 micron emission, a lack of mid-infrared emission, but it just means a lack of mid-infrared emission above a certain level, which says that it's bright enough to be protoplanetary. So it just means that there's a low amount of 24 micron emission. So it's still there, it's still present for 20% of stars, but they are a mixed bag as well. It's not, so they look like there are some that look like they could be debris disks, the very youngest debris disks that we see. There are some that have what looks like very warm emission, and these could be dust that is coming from the kind of planet forming collisions that you expect from the terrestrial planet forming regions. It could be warm dust, because when the protoplanetary disk disappears, there could be a bunch of planets there, and they then go unstable and undergo an epoch of collisions, and we could be seeing that dust. And then there are another a bunch that's like this one that has the gas that's outflowing, that could be gas disk, the final stages of the dispersal of protoplanetary disks. So we could be seeing quite a mixture in that class. I think it's a very interesting class to understand the evolution.
Can I interject quickly? I completely agree with you, Mark, and I would like to suggest, I really love this service. I would like to suggest to add some accretion diagnostics when you look at the class 3 sample. I think that's also important to look at the evolution of the gas, because in the debris stage, right, we don't see anymore that type of accretion. And maybe in these class 3 groups, you may have also very low accretors. And I think that's interesting to look at that as well.
All right.
I thought that the class 3 was always defined also by the X-rays, that they showed up in the X-ray surveys, but that has not been used recently so much as in, I think, the early days.
No, but by definition, the class 3s are ones that have they're defined by their infrared excess. But then there's also the weak line T-Tauri. It's kind of, there's some confusion, of mixing of the groups, but we try to make it very clear, how you define what's a class 3, because actually there are other surveys that people have done that say is a survey of class 3 stars, but they're class 3 stars that have detectable 24 micron emission. There's different types of class 3. So you have to be very, very careful about how you're defining the samples.
Right. I think that that just goes to the point that our nomenclature for the transition from protoplanetary disks to the more advanced stages is quite a mess, actually, and does need some clarification. So there are a number of hands up. Let me go through. Amelia, you're next.
Yeah, I wanted to make the point of weak line T-Tauri and accretion, and if you select based on X-rays, if you select based only on 24 micron, or if you are going farther in the wavelength range, but also that I think I love surveys, so obviously I like surveys of class 3 objects a lot, but I think sometimes we don't compare fairly in the sense that we don't reach the same masses. So we are comparing younger disks to lower masses, then debris disks to higher masses, and we build evolutionary sequence that are not comparing objects that evolve at the same rate.
And we neglect sometimes because we cannot incorporate it, but multiplicity at all ranges. I mean, we have studies of tight multiples, how do they affect very wide multiples, but we really, I mean, we have a continuum, right? So, and that affects differently at different masses because also multiplicity rate is different for different masses. So I think the masses of the objects and the particularly different evolutionary paths that this imprints should come into the picture also.
Indeed, it's a multi-parameter issue with multiplicity and host stellar mass and many other factors, and we need very large samples, I think, to piece all that together. Antonio, you're next.
Yeah, so I know that most of us are skeptical about evolutionary tracks, but somehow I want to say, I mean, independent studies, maybe it's on astroseismology, or comparing dynamical masses, I mean, tell us that, yeah, maybe evolutionary tracks are wrong by something, but not particularly wrong, extremely wrong. So when we think of this very late class 2 disks, they are maybe 8, 10, 12 mega years old according to our tracks. This is telling us that this is true. Even some recent studies on HD 139, 614 by Morphin collaborators tells us that these are 10 mega years old disks. So if we look at the distribution of this very late class 2 disk, all of a sudden at 15 mega years there is nothing. So that means again, going back to the talk by Barbara, there must be something that keeps, you know, this class 2 existing until 10, 12 mega years, and then all of a sudden they disappear, and there is no late class 2 disk at 15 mega years. So yeah.
Right, James.
Yeah, thanks. I just wanted to highlight again the need for uniform deep class surveys of class 3 disks, both in dust, gas, and accretion would be extremely useful for the disk dispersal models, because at the moment the canonical disk dispersal model, the photoevaporated disk dispersal model, fails to explain the the statistics of transition disks at large radii, or the disk dispersal phenomenon that's going on at large radii. It sort of predicts that there should be a longer lived phase of disk dispersal at large radii, and that's simply because that's where a lot of the mass of the disk resides, so it takes longer to remove it. And knowing from the observations exactly what is going on will help us fix these models. So is it the dust that disperses first? Is it the gas that disperses first? Do they disperse together? And so on. And what do they leave behind?
Right. Ilse?
And just quickly, adding on to that, don't just rely on CO, as you've heard many times, as your gas tracer. Just to advertise a nice paper by Dana Anderson last year showing that there were some disks in upper SCO that have very bright N2H+ relative to CO. So these would be disks that would not, if CO were truly tracing gas, would be thought to be gas poor, but they have very bright N2H+. So consider your gas tracers carefully, but it would be great to just have the data, I agree.
Yeah, let me just add carbon-1 also in this respect, because I think especially for the debris disks, actually also carbon-1 may be a good tracer if CO is photodissociated, and that might also be an option.
Right. I wish it were a little easier to observe.
Yes. Hey, we're on Chestnut Tour. That's so we put Alma as high as we could. That's for exactly that reason.
Right. All right. Well, since we are talking about disk dispersal, let me just bring up one of the other questions, which I think is also a bit provocative, which is do transition disks represent a distinct evolutionary phase? James already said a little bit about this, but what are the classic transition disks? Oh, there's a brave one, Barbara. Oh, need to unmute.
Yeah. Well, again, I don't know the answer. So because I don't know the answer, I actually put it in a poll. No, what are actually transition disks? What are real transition disks, and what are just long-lived objects that have a cavity of some sort. So it seems that the people have spoken to say that those the real transition disks are only the ones that have low accretion rates and also small cavities or smaller cavities, and those huge beasts that are imaged generally with ALMA, which are very large millimeter fluxes and have large cavity and high accretion rates, are a mixture of many things. So people said, depending on the object, they may be rare objects, which are, however, long-lived, and so not really objects in transition, but just objects with a dust trap in them. Other objects may indeed be objects in transition made by different processes. So I think this kind of reflects also my opinion on that, it would be nice to know which objects are really representing disks on the last gasps of their lives. And I think for that, we have to concentrate on those with lower accretion rates rather than those with huge accretion rates and large cavities, which mean that they have a lot of thick gas in the inner parts.
Any other comments on the transition disk phase? All right, since I'm not seeing hands, I'll extend that to say, are the transition disk structures related to the structures that we see in debris disks? Some of the debris disk experts may want to weigh in. All right, Seba.
So by structure, exactly, David, do you mean multiple rings, gaps?
Could be multiple rings, something you know about. Could be single rings.
Yeah, so yeah, as you know, right, with ALMA, we have basically been able to show that debris disks in general are wide-ish. The picture that most people have of these very narrow disks like Fomalhaut or HR 4786, one of the first ones to be imaged, are very rare, and most of them are white. So that means that there's a lot of space in those disks to have gaps. And so far, the white disks that we have looked at with enough resolution and sensitivity seem to show substructure. The only disk that I can think of that doesn't seem to show that, perhaps, is HR 8799, but that's a work that will come out soon. But all the rest seems to show like substructure, and that, in my opinion, means that there must be some connection, right, between the two. And how exactly that happens is an open question. I could say more things about that, but
I think there's also an interesting discussion going on actually in the chat. I think Nienke is contributing there to some of the discussion, even though we can't unmute her. But
right.
And so those of you who are interested in some of these points, keep an eye also on the chat. There's interesting things going on there. But Mark, I think, wants to contribute as well.
Yeah, please go ahead, Mark.
Yeah, I mean, what we see in debris disks has to relate to protoplanetary disks at some level, but we need to have a study of the fraction of stars that have rings in protoplanetary disks at different radii and how that relates to what we see in debris disks. But the problem is that we still only have debris disks imaged and known around 20% of stars. So we only know where the debris disks are around 20% of stars, and the rest of them could have disks that are faint and could be at any other radii. So we're a bit stuck with that. But what we do know, we have the planets, how they relate to planets, and we know more about that. And in that respect, there's no correspondence, real good correlation with the debris disks we know with the planets, apart from the fact that there are planets within them. There are planets that are massive, you know, like the Beta Pic planets or the HR 8799 planets, but then there are also super Earth-like planets that are, you know, the compact, tight systems that you see, kind of systems you see with Kepler. So I think the debris disks are found around a whole plethora of planetary systems, and probably also form in a range of protoplanetary disks, not just an exact one-to-one correspondence. Although that would be nice if we could say that.
Right. I suppose part of the question is to what extent do the dynamics of planetary systems shape the debris disks as opposed to the initial conditions from the protoplanetary disk stage.
Yeah, that was a good question that I think came also up. To what extent is that all inherited? So, or to what extent is it reshaped? Yeah.
Right. All right. Well, maybe that's a good segue to the final topic, which is exoplanets. One of the questions, which I think unifies a number of the topics in this session, is are snow lines important for setting exoplanet compositions? And do we have any hands raised to address that?
And let me just add to that, because I think this question is important in relation to the dust traps that we were also talking about, because I think it's especially the relation of dust traps with respect to snow lines that can be important here. So Lukas is the first one to address that. Yes?
Well, the short answer will be for me, yes, because I mean, I would believe that the snow lines are crucial to setting the gas and the dust composition in the disk. So, and especially for the warm disks, and the location of the snow line will be crucial for example, determining where the planet is getting bulk of its mass. But I think it's also important indeed to understand how this composition can evolve with time, and how it will change, and indeed how much of the dust can drift inwards, and that will also make a big change if there are dust traps involved. But there are probably more experts on that area.
Yes, I see Coco already with her hand up. So Coco, take it.
Yeah, so I definitely think snow line sets important boundaries for different ice species in the solid phases. Also, I think it's very interesting to think about in the new picture of the pebble drifting and pebble accretion scenario of planet formation. So as Ilaria just said, so there are some hints of the water enrichment in some small disks. So I think pebble accretion planet formation models, they generally require a huge amount of pebble drift inwards to make the pebble accretion work. So it has enough mass supply. So it's very important to say in the new aspects of the dynamic involution of a disk formation, how the snow line sets the different ices and the gas, carbon, oxygen budget in different regions of disks.
Yes, just to add to that, I mean, you mentioned indeed the recent Banzatti result on the water, potential water enhancement in the inner disk, as you expect from drifting icy planetesimals or pebbles. There's also evidence from the CO in some disks of the carbon. But on the other hand, there are also now quite a few disks where actually the opposite is seen in the inner disk, where you have a low carbon abundance or oxygen abundance. I'm thinking of TW Hydra, the work by Bosman and Banzatti. I think the work of McClure of measuring various atomic lines actually coming from the inner disk carbon. So there are also a number of disks where actually it's underabundant. So suggesting dust traps basically outside the ice lines of those major species. So what is the interplay between those two? I mean, Ilaria, did you want to comment on that as well?
Now, you have a very good point, and I cannot further expand on that. I wanted to make a comment on the importance of ice line and formation rather than composition, because I think this result was not mentioned in the conference, but there is an interesting let's say, so the occurrence of giant planets has been recently modeled by Fernandez and collaborator, taking into account the biases of the survey, the radial velocity survey, and it looks like there is a peak around what is potentially the snow line of, sun-like stars. So I think it is quite interesting that this connection between more giant planets at the location of what is potentially the snow line. And this result is being now confirmed by the Keck exoplanet survey. So
this goes back to the original idea of Donin and Stevenson, that's yeah. Having basically the
announcement. Yeah. So it's an old idea, but I think it's interesting, right?
If there would be observational hints for that, that's very important. So, I mean, exoplanets, do they get most of their heavy elements actually from the dust or from the gas? Who can speak to that? Yeah, Lukasz.
Yeah, I mean, I would say, given the ratio of how hydrogen dominates the gas phase and how little of the rest of the material is metals, actually, I would say the solids are a crucial component. And even outside of the early core, if we go to the envelopes of the gas giants, the bulk of the solids inherited there, I would assume also to come from the dust and the ices that they have on. But maybe there are more comments on that.
He also wants to add to that. I think we're rapidly running out of time, so let's keep it short.
As a quick comment, for me, the HR 8799 system, where we have these multiple gas giants with different C/O ratios inferred for their atmospheres. I'm not an expert in the modeling, but that to me, says that there is a role for both the gas and the dust and how they're partitioned spatially. It's pointing away from something like gravitational instability, more towards something like core accretion. But I think that's a really interesting system for us to be trying to understand better, because we have spatial information on these different C/O ratios.
Right. Beta Pictoris is another one that is very interesting, and that is Beta Pic B and Beta Pic C. That's beautiful gravity measurements, field-theory gravity measurements of that now. But even within our own solar system, how did Jupiter get its elements? There are several papers by Karin and others that Bosman et al. That point to Jupiter being formed much further out. So who knows? Based on the nitrogen, actually, that's another interesting element. Good. I think we still have another 3 minutes. So this is really your opportunity, or from the people on Slido, to put in something still that is really very urgent to bring up that we haven't touched on yet. A burning question that you have. Silence.
If no one wants to say anything, I have a suggestion. I have just created a poll very quickly using one of the questions that you mentioned, one of the points that you brought up, which is whether transitional disks are really a transition. So I'm just going to put it there. Do we need to start calling transitional disks differently? I'll leave it there, see what people vote, and then you can comment on it.
All right, very good. Let's see who's still awake. We still have 195 people on the online.
Right.
So
it's fun to see the answers evolve in real time here.
Yes. Yes, Enrique, maybe you can start putting that on the, see that's evolving. You can put it on the screen.
Can I say something while people vote?
Sure.
No, I just saw that one of the most voted questions is whether compact proportionality disks, if they have the same structure as the large well-resolved disks. I just want to say that's a question that I'm really interested in, because at the moment we just don't have the spatial
Yeah,
resolution.
I don't think we have the data for that. I saw that question as well, but I don't think we have the good data yet. I think that will be coming. I know that there are several programs in the ALMA queue, so we really hope that ALMA starts observing again.
I do think
I was
going to say, I do think there's more to say about that, but perhaps that should wait for the substructure discussion.
Yeah, exactly. That's so it's a good question, but I think it's waiting for some more data and also for the next panel session. Yeah. Good. So here we have the poll, and there were still 2 people that had their hands up. I've now lost my hands up view.
Don't see any.
Don't see any. Okay. All right, but now if you have cavity disks, then the question is cavity disk versus gap disks. That's so that is going to be also maybe something for the. I think this actually should be taken to the next discussion session. The session 2 would be good to continue on this topic because structure comes in here, substructure. Okay, if there are no other further comments or questions, then shall we call it a day, a night, a morning, depending on where you are in the world. It has been a good discussion.
Yes,
so for 1.5 hours, thanks everybody to the panel for that. Yeah, let's clap actually. let's clap especially for all the speakers. Several of you are actually speakers. Please continue to look through at the Slack because there are lots of good comments there as well. And don't forget to look also at the contributed talks. Those may answer actually some of the questions that we have posed here. So thank you very much from my side. Back to David and to the organizers.
Yes, thanks everyone. This was a wonderful discussion. This whole conference is fantastic. It's just great to see all these new results in so many different formats to keep up with. So I'll just toss it to Enrique if you have any announcements.
No, I don't think I have any announcements. I just want to thank you two, David and Edwin, for moderating this discussion. It's a different format, so it's quite a task. And also, I want to thank all the panelists for participating in the discussion. This was very great. I think this was very interesting. Thank you, everyone, for attending. And tomorrow we'll start back again at 3 UTC. But before that, we're going to go into a break now because we're going to have some short presentations. So if you want to hear more about some contributor talks and posters, stay tuned. Let's go into a 15-minute break, and we're going to come back at the 15 past the hour.
All right. Bye-bye, everybody.
Bye-bye. Thank you.
Bye.
So we're back. Welcome everyone to the third and last short presentation session of the conference. I want to remind the participants today, as usual, keep in mind that it's going to be a minute and a half, and we'll have to move on if you go over the time. So I'm going to share my screen. Okay. Oh, wait. I don't think you can see the timer, can you?
No.
Let's see. Okay, that's it.
There you go.
Better now?
Yep.
Okay, so the first speaker today is Elizabeth Arthur. Are you ready, Elizabeth?
Yes.
Please go ahead.
Okay, hi everyone. My name is Elizabeth Arthur de la Villarmois, and in my talk I will present the results from an ANMAR survey of 10 class 1 sources. In particular, I will discuss our results from C17O and SO2. C17O is a disk tracer and allows us to estimate the protostellar mass from position velocity diagrams, and we find a linear correlation between the protostellar masses and the mass accretion rates. We also see that the mass accretion rates of class 1 sources lie between 10 to the -7 and 10 to the -6 solar masses per year, which is an observational evidence of a variable mass accretion rate. SO2, on the other hand, is a shock tracer and shows compact and high velocity emission, which is not consistent with the Keplerian rotation. So we propose that this SO2 emission is tracing accretion shocks between the envelope and the surface layer of the disk. SO2 also, if we plot here volumetric temperatures and volumetric luminosities, we find that SO2 is tracing the higher, is associated with the highest mass accretion rates, also related with the higher volumetric luminosities. And then this will go back to like SO2 is tracing like the envelope in accretion shocks, and also C17O higher mass accretion rates. So we later compare with the theoretical models here. So if you're interested, please come and see my talk. Thanks.
Okay, thank you very much, Elizabeth. Next speaker is Yashin B. Yashin, are you? Yeah. Okay. You ready?
Yep.
Here you go.
Hi, I'm Jiaxin B from the University of Victoria. Here, I would like to advertise for our recently submitted work in which we challenged the idea that dust grains of sub-millimeter and larger sizes should stay in the disk midplane. We show that sub-millimeter dust grains can be stirred up to high disk elevations when a gap opening planet is in the disk. Here is a snapshot of the dust-to-gas ratio from our 3D global hydrodynamic simulation, plotted in the radial and vertical plane and averaged azimuthally. We put a Saturn mass planet at the reference radius 1 and see that dust grains with Stokes number of roughly 10 to the -3 at both gap edges can be stirred up to as high as 2 scale heights. We found that the dust puff-up phenomenon originates from the meridional gas flows driven by the gap opening planet. We also found that planet mass and grain size can affect the puff-up pattern greatly. Given that the HL tau rings are considered to be well settled to the midplane, this study might be able to help to constrain planet mass or dust grain size in the disk. Well, if we assume that the rings are produced by planets in the first place. For more detailed analysis and explanations, please go and check my video, and I'll be happy to chat in the Slack channel. Thank you.
Thank you, Yashin. The next speaker is Gemma Busquet. Gemma, are you ready?
Yes.
Okay, please go ahead. Yes, all fine.
Okay, hello everyone. I'm Gemma Busquet from the Institut de Ciències de l'Espai in Barcelona. In this talk, yes, I don't. Well, in this talk, I present the results from very sensitive polarimetric ALMA observations toward the high mass young stellar object GGD27 MM1 that powers the spectacular radiojet HH8081.
The high spatial resolution reached by these ALMA observations of about 56 astronomical units allow us to clearly resolve the disk in this massive object, which is oriented perpendicular to the jet. We model the disk using the irradiated alpha accretion disk models developed by Paola D'Alessio, and find that the disk is compact, very massive, and also very, very warm. In addition, we also obtain very important constraints on the dust properties, such as the dust setting and the maximum grain size from the dust polarization measurements. And finally, we also discover a cluster of 25 disks around class 0 and class 1 protostars, thanks to the extraordinary sensitivity that we reach. So if you want to find out more details of this work, I just go and check this talk. Thank you very much.
Okay, thank you, Gemma. Our next speaker is James Catman. Are you ready?
Yep.
Please go ahead.
So hi everyone, I'm James Cadman from the University of Edinburgh. My research is into planet formation, the evolution of protoplanetary disks, and in particular focusing on very young disks which may be massive enough to be self-gravitating. And in my talk we use semi-analytic models of self-gravitating disks coupled with radiative transfer models and a tool for simulating ALMA observations to make observational predictions of these systems. And in particular we focus on the role of dust trapping in these systems. So in protoplanetary disks, you get rapid migration of millimeter and centimeter grains from the outer regions to the inner regions. And in a self-gravitating disk where you have these self-gravitating spirals, these migrating grains will pile up at the pressure maxima in the spirals. And so you get high concentrations of these millimeter grains in the spiral regions, you get enhanced emission. Equally, you get depletion of these same particles in the internal regions. And ultimately, this may have important consequences for our prospects for observing these systems, these very young systems in this brief self-gravitating phase. We also use these models to analyze 3 disks from the D-sharp survey and attempt to place constraints on the gravitational instability as a plausible mechanism for driving the observed spirals in these systems. So if this sounds interesting, then please come and check out the talk. Cheers.
Cool. Thank you, James. The next one is Carlos Carrasco Gonzalez. Carlos, are you ready?
Thank you. Yes. So hello, everyone. I'm Carlos Carrasco Gonzalez. I work in the Institute of Radio Astronomy in Mexico. So some of the main questions we are discussing here are how fast dust grows in this, what's the role of substratus in this process, and what's the origin of substratus. So an answer to this question requires to investigate the particle size distribution in this with the highest angular resolution possible. However, this has revealed not easy even with ALMA because of 2 main reasons. Emission at millimeter wavelength seems to be optically thicker than we expected, and dust scattering seems to be very important in this. We found a solution for H tau, since we already have several high-quality ALMA and BLA images for this disk covering a wide range of wavelengths. This is covering a wide range of optical depths. From this, we can model the SED at each radius, not assuming optically thin emission, but modeling the optical depth with frequency. We also consider the effect of dust scattering in the dust opacity. So the result of this is that we can measure dust properties, temperature, density, and maximum grain size at an unprecedented high angular resolution for a disk. Our important results are that we find millimeter-sized particles everywhere in the disk. These are not centimeter size like in other disks, but remember that H tau is a very young disk. Bright rings contain bigger particles, dark rings are smaller particles. This confirms that rings are accumulated and growing dust particles. And something important is that the internal substructures seem to be associated to ice lines of some molecules. Thank you, and please take a look at our posters and paper.
Thank you very much, Carlos. The next one is Daniel Carrera. Daniel, are you around?
Yeah, I'm here. Hi.
Okay.
So, hi everyone. Well, I'd like to present the first evidence that a pressure bump like the ones that we see in ALMA in H tau can trigger planet formation by the extreme instability. Now, the idea that a pressure bump itself can trigger planetesimals is itself not new, it's very old, and several people in this call have already thought about that.
But what we have done is we have run the first high-resolution 3D simulations of a really long shearing butt, big enough to contain a pressure bump as similar as we can make it to the ones that we actually observe in HL tau, and with a realistic particle size based on the fragmentation limit, a realistic dust-to-gas ratio, Sora-like value, we did in fact see gravitationally bound planetesimals forming by the streaming stability. We also tried smaller millimeter-sized particles. Those didn't form planetesimals. We're not sure whether this is a numerical artifact or if it's like a real problem and really small particles really can't form planetesimals. We're doing additional simulations to look into that, and we'll get back to you. And I hope you take a few minutes to look at my talk later or speak with me on Slack. Thank you.
Cool. Thank you very much, Daniel. The next speaker is Thane Curry. Thane, are you there?
Yes, I'm here.
Great.
Yeah, okay, so the presentation on my talk channel focuses on Skexio-Keras direct imaging of candidate embedded protoplanets in transitional disks, right? So we know that nearly all stars are born with gas and dust-rich disks that may form the building blocks of planets, and many planetary systems are common, and including some planetary systems have wide separation, massive directly imaged companions. So we'd like to be able to see how we incorporate the seed material for planets into the finished product. The way we endeavor to do that is to be able to image structured transitional disks. And in particular, we focus on systems with claimed protoplanet candidates in the literature, and then also other structured protoplanetary disks that may be interesting to follow up. So our first result focuses on Lookout 15, which had 3 planet candidates identified from sparse aperture masking interferometry. What we instead find is that the claimed protoplanets appear to form the forescattering edge of an inner disk component. We also have unpublished data for MWC 758. This is another system with a candidate protoplanet. Instead, we find no evidence for a planetary signal at this location. It's unclear exactly what this signal is responding to. The most exciting result, I think, though, is a new candidate protoplanet we have identified now from 12 different data sets over the course of 4 years with Skexio. Its spectrum appears to be non-disk-like and appears to show evidence for orbital motion. If you'd like more information about that, please visit my talk channel. Thank you.
Great. Thank you, then. Next speaker is Joanna Dratkowska.
Yeah, thanks.
Okay,
yes.
Go ahead.
Hi, my name is Joanna Drążkowska. I'm a postdoc at LMU Munich, and my talk is about planet growth by pebble accretion. So most of you probably know that pebble accretion is one of these big developments in planet formation theory that started to gain popularity around the same time as the HL tau image was released. And then people noticed that rocky cores of planets may grow much faster if they accrete those pebbles that are seen in the disks, rather than larger planetesimals. And planet growth rate in these models is very sensitive to the amount of pebbles that flow past the core. However, when I was reviewing papers on pebble accretion, I noticed that most of them would use rather arbitrary values for the pebble flux. So I decided to check what would be coming out of our dust evolution models done with the dust bytecode. And I also calculated planet growth myself, as you see here in the left plot. And the results change a lot with the level of dust fragmentation, which is a very uncertain parameter. In the right plot, you see the pebble fluxes that I get in my models. And if you would like to check what would be a realistic pebble flux in your favorite disk model, then you can use the script that I have written called Pebble Predictor. And of course, if you want to know more, then please see my talk. Thanks.
Great. Thank you very much, Joanna. Logan Francis is the next in the list. Are you ready, Logan?
Yes. Hello?
Go ahead.
Oh, it's already up. Okay, excellent. Hi, I'm PhD student Logan Francis at the University of Victoria, and my talk is on a recently published paper that I wrote with Ninka van der Merel, where we used archival ALMA observations of 38 transition disks to investigate inner disks inside the transition disk millimeter dust gap. We found that there were inner disks detected in about half of the sample,
And for some of those inner disks, we also had enough resolution that we could actually resolve them and place some constraints of the size and inclination, and found that some of them were misaligned with the outer disk. We did some simple analytical radiative transfer calculations and found that the inner disks were mostly optically thin and used that to estimate dust masses, and found a range of about 2 orders of magnitude for the inner disk masses, but also noted that given the heterogeneity of the sensitivity in the archival sample, that there could actually be many more inner disks that we did not detect in the less sensitive observations. We found that the inner disks sizes and luminosities were consistent with a scenario where the sizes were determined set by radial drift, and where the millimeter grains were decoupled from the accreting gas. And finally, for PDS-70, we found its inner disk was actually an outlier in the sample, and suggests that perhaps that the planet in the PDS-70 gap has only recently opened it and is bright and actively accreting. Thank you for your time, and please check out my talk.
Thank you, Logan. Next one is Jane Huang. Jane, are you ready?
Yes.
Please feel free to go ahead.
All right. Hi, everyone. I'm Jane Huang, a Sagan Fellow at the University of Michigan, and I contributed a talk about recent 12CO ALMA observations around the T-Tauri stars, Aryelope and Giamaraghi. So on the left side, you see the millimeter continuum from D sharp for Aryelope in orange, and our 12CO ALMA observations in blue, which were published earlier this year. And whereas the millimeter continuum is compact and axisymmetric, you can see that the 12CO emission traces multiple irregular spiral arms stretching out to about 1,000 AU in conjunction with clumpy emission. And likewise with Giamaraghi, the continuum is largely axisymmetric and multi-ring, but the 12CO emission, which is shown on the same scale, is much more extended. This 12CO observation comes from the Cycle 6 Disk Chemistry large program MAPS. And you also see a couple spiral arms as well as some more extended tail and streamer-like structures. And these observations in conjunction with what people have been seeing in protostellar disks suggests that disk gap and ring structures can form under much more, form and evolve under much more complex conditions than are normally assumed. And that furthermore, this diversity of structures that we're seeing even in a limited sample of disks points to the need for more deep 12CO observations with ALMA in order to probe the full diversity of planet-forming environments. Thank you.
Thank you, Jane. The next one is Eric Jensen. Eric.
Hi, everybody.
Ready?
Happy to talk to you today about some work that I'm doing with Rachel Akeson to try to answer the question whether two disks in a binary system are aligned with each other or whether they're misaligned. You can see some of our data here on the left-hand side. This is CO data. You can see the velocity maps. I'd like to call your attention to the redshifted side of each of those disks. And you can see that in many of those systems that the emission is pointing in about the same direction. Disks are not perfectly aligned. But what we find interestingly in a modest size sample is that they're more aligned than not, more aligned than they would be in a random distribution. Certainly there's some that are misaligned in the lower right there. You can see WSB 71 is not so well aligned. This is quantified in that plot in the right-hand side. So there we're showing the position angle difference in a given system. So aligned would be on the left-hand side, misaligned would be towards the right. If disks were randomly oriented, it would follow that orange line. The data are in blue, and you can see sort of a pile up of kind of 10 to 20 degree misalignments, but more aligned than you might think. This is actually consistent with formation of misaligned disks that's predicted, that then comes into alignment as predicted by some work by Lubo and Ogilvy, and more recently Fukar and Lai, to evolve towards alignment. If you'd like to know more, please visit my poster in Slack. Thanks.
Thank you, Eric. The next speaker is Cristiano Longarini. Cristiano.
Hello. Hello, everyone. My name is Cristiano Longarini, and I'm a first-year PhD student at the University of Milan. And in my poster, I presented my first work, dust rings formation in misaligned circumbinary disks, which has been done with the collaboration of Giuseppe Lodato, who is my supervisor, Claudia Toci, and Osama Ali.
We considered a misaligned circumbinary disk, and we found a dynamical dust trapping mechanism without the presence of a pressure maximum that allows the creation of two dust rings in these systems. This effect is mainly due to a difference in precession rates between gas and dust that induces a geometrical difference of speed, which can balance the physical one due to the pressure gradient into location inside the disk, where the total difference of speed is zero, and thus the radial drift does not act. We performed an analytical study and numerical simulations of this mechanism. And for further information, please see my poster, and you can also write me on Slack for questions or for advices. Thank you so much for the attention and for the opportunity to speak.
Thank you, Cristiano. Next speaker is Joshua Lowell.
Hi, everyone. I hope you can hear me. I'm Josh. I'm a third-year PhD student at the Institute of Astronomy in Cambridge, where I'm basically looking at the evolution of planetary systems. So on Monday, we saw a talk on debris disks. Yesterday, we heard talks on disk evolution, and tomorrow we're going to be hearing more about planetesimal formation. And this afternoon, throughout the discussion, we heard about class 3 stars, what they mean for disk dispersal and evolution. Well, put all of those into one talk, and this is what I'm providing here. So this talk is about the most recent results of 2 papers that we've had accepted, one on a survey of class 3 stars and the other one on outflowing gas from one of those. So we find detections of potentially the youngest debris disks that have been observed in ALMA, with ALMA, sorry, in Lupus. And as I say, one of them has gas and it has a unique outflowing signature, which we believe might be may be a very unique source. So if that hasn't interested you, what I can guarantee you is ALMA images of disks and gas. So yeah, please come along, watch the talk, join the channel if you've got any questions. So I'll stop talking there. Thank you.
Thank you, Joshua. The next on the list is Enrique.
Hi, everyone. I'm Enrique Matias. I'm an ALMA fellow in Santiago, and I'm presenting a poster titled Characterizing the Dust Content of Disk Substructures in TW Hydra. So in this study, we analyzed archival high angular resolution observations with ALMA at 0.87 millimeters, 1.3 millimeters, 2 millimeters, and also we paired them with new observations at 3 millimeters. We analyzed the multi-wavelength emission, and we obtained radial profiles of the dust temperature, dust surface density, maximum particle size, and also the slope of the particle size distribution. So the main results that we find is first that the disk is optically thick, meaning that the tau is larger than 0.9 millimeters and 1.3 millimeters, up to 55 AU. In the near 20 AU, the disk is optically thick even at 3 millimeters. This results in we're not able to characterize the dust content in these regions, so longer wavelengths are needed, VLA. The maximum size is larger than 1 millimeter, but interestingly, we cannot fully constrain the maximum particle size if we let the slope of the particle size distribution vary. But we find the large particles are accumulating at the rings, meaning that we find high dust surface densities and flatter particle size distributions in the rings. We measure a total dust mass between 250 and 330 Earth masses, meaning that the global gas dust mass ratio would be between 50 and 70. And we find a higher dust mass than what you would obtain just from the similar flux. So if you want to talk more about this, please come to the Slack channel of my poster. Thanks.
Great. Thank you, Enrique. The next one is Karina Malco. Karina, you ready?
Yes, yes.
Please go ahead.
So, hi, I'm Karina Malco. I'm a postdoc in Universidad del Paraíso and also a member of the MPF in Chile. In my talk, I want to talk about this study on the joint transitional disk in lupus. We observed with ALMA 2.1 millimeter. It hosts one of the largest cavity around the Tauri stars. You can see that has a ring shape. And we want to study the dust grain. So we estimated the spectral index using archive ALMA data. And we found that the spectral index is 3.4 and is basically constant throughout the dust region. So that's peculiar. If we assume optically thin emission, we found a dust opacity coefficient that is 1.4. So if you compare it with different disks in different regions, you can see that this disk has one of the largest values of beta
and also compare it to the different disks in the lupus region. Of course, we need longer wavelength observations in order to prove better the beta coefficient. And even though high beta might imply small grains, when we use the D-sharp opacities, for example, we found a maximum grain sizes in the order of millimeters. So we need longer wavelengths to try to improve our constraints in MX, but this is a very interesting source. So if you want to know more about it, go check my talk, and I'd be happy to answer any questions in the Slack channel. Thank you.
Thank you, Karina. We move on to Marveli Mikolta. Marveli, are you ready?
Can you hear me?
Yes, we can.
Okay. Hi, everyone. My name is Marveli Mikolta. I'm currently in my last semester of my physics undergrad at Universidad de los Andes, Venezuela. So the accepted model for mass loading onto a star is a magnetospheric accretion model in which the material falls onto the star along the field lines. We use new indicators, the calcium 2 lines, H and K, and the infrared triplet lines to probe the geometry of the magnetosphere and its dependence with the mass accretion rate for extremely large grid models with the chameleon-1 star forming frequent observations. So this is important because the integration of the emission lines formed in the magnetosphere provides the mass accretion rates, which is crucial for obtaining this structure, as we have seen in this conference before. So we find an agreement between the models inferred from the lines, and the results suggest an inverse correlation between the mass accretion rate and the disk truncation radius. So if you want more details, please check the poster and I'll be happy to take any questions. Thanks.
Thank you very much, Marveli. Next one is Joan Najita. Joan, are you there?
Yes, I am. Can you hear me?
Yes, please go ahead.
Awesome. So my poster is about observing disk accretion in action, and it addresses the question of how disks accrete. We know that disks are accreting because we see accretion onto the star, but how does the matter get there? What the big problem is exactly what's going on in the planet formation region of the disk, where between 1 and 30 AU, where the disk is very thick, it has a large column density, and has to rely on external sources of ionization, which are limited. So people have said that the magnetorotational instability is having trouble here, and MHD winds may be needed to solve the problem. One way to look at this problem is to look to try to see what's going on in the disk, whether we can see any evidence for disk accretion. So I wanted to share with you the results for this one class 1 source, which reveals redshifted acetylene, HCN, ammonia, and water lines, redshifted at high velocity by 4 to 20 kilometers per second. The abundances and column densities are consistent with the absorption occurring in the inner disk and flowing in at supersonic velocities at inflow rates comparable to T-Tauri accretion rates. These kinds of flows are actually seen in MHD simulations of including those driven by magnetic winds. And so potentially this is a way to observe disk accretion in action. Thanks.
Thank you, Jen. For the next one, James Owen. I see you there. Okay.
Yeah. Hi, everyone. Like many of us, I was utterly enthralled by these high-resolution images of protoplanetary disks that Alma has been giving us, and particularly the sort of ring structures. And one of the suggestions for this is these have been caused by snow lines. So what I've been doing is exploring this mechanism in more detail. Now, as we all know, snow lines are caused by a change in temperature. So when the temperature drops below a certain threshold, the volatiles can freeze out into the solid phase. But the fact that the temperature of the disk is determined by how much radiation the solids can absorb means that this process is actually intimately coupled, that if you freeze volatiles out into the solid phase, you change your abundance of solids, which is naturally going to change your temperature and maybe change where the snow line occurs. And in thinking about this process and coupling these two mechanisms, the temperature calculation of the disk with the amount of solids, I've realized that the snow lines are probably thermally unstable, in that if you start freezing out, you increase your amount of solids, you cool the disk, and you just freeze out more. And this actually causes the snow lines to be sort of processes that move in and out. They don't occur at fixed locations, and you can actually just study this in terms of a classic thermal instability limit cycle. So take a look at my talk, and I'm happy to answer any questions.
Great. Thank you very much, James. The next speaker is Yoko Oya. Yoko?
Hi, can you hear me?
Yes, all fine. Please go ahead.
Yeah. Hi, everyone. I am Yoko Oya of the University of Tokyo in Japan. We have observed this class low mass protostellar source with ALMA. IRAS 16 to 93 minus 2422 is a binary source, and one of its constituents, source A itself, is a closed binary or a multiple source. We have delineated the kinematical and chemical structures of its disk-forming region with a spatial resolution as high as 10 AU. The main results in my talk are listed here. First, the multiplicity of source A is clearly delineated in the continuum emission. Second, both the circumultiple structure of source A and the circumstellar disk of the protostar L1 are detected in molecular lines. We modeled their kinematic structures. Third, the outflow structure is traced by the SO line, and its rotation motion is detected. In my talk, I compared the specific angular momenta of the gas of the disk envelope system and the outflow, and discussed their mutual relation. I am looking forward to having your questions and discussing with you. Thank you.
Thank you very much, Yoko. The next on the list is Linda Podio. Linda, go ahead.
Yes. Hi to everybody. In my talk, I try to briefly summarize the main result of the ALMA chemical survey of disk outflow sources in Taurus. So what is the goal of ALMA? The goal is to characterize the chemical composition of young disk to understand what chemical content is inherited by forming planets. As ALMA has shown that planets form in disk younger than 1 million years, this is why we decided with ALMA to target young disk. And you can see on the left the 6 disks covered by our sample. However, when we target young disk, the problem is that the CO emission, as you can see in the second column, is completely dominated by envelope and outflow emission. However, in CS and formaldehyde, we beautifully trace the outer region of our disk, while the inner region is hidden by optically thick dust in the disk or by absorption by circumstellar material. I want to drive your attention on the fact that we also have 2 detections of H2CS in our sample, and Claudio Codella has uploaded a talk about this, and we also have detection of methanol. And what we try to do is to estimate the abundances of our molecules and to reconstruct the chemical path from hot Corynus around +0 sources to +1, +2, and finally we also compare with the cometary abundances. So please go look at my talk and let me know about your question. Thank you.
Great, thank you very much, Linda. The next one is Alejandro Santamaria Miranda. Alejandro, are you connected?
Yeah, here I am.
Yeah, please go ahead.
Hi, my name is Alejandro Santamaria Miranda, and I am an ISO fellow in Chile. So we use ACTEC single disk observations to identify cores in the substellar regime in Lupus 1 and 3. We combine these cores with previously known class 2 brown dwarfs, and then we observe them with ALMA at 1.3 millimeters. We identify 19 sources that covers from presubstellar candidates to class 2 sources. Our objective is to identify the main formation mechanism of brown dwarfs. They can form similar to stars as isolated sources or similar to planets in protoplanetary disk and subsequently ejected. We have 3 main results. In the left bottom, we can see the presubstellar cores that are compared to a gravitational density profile, and we see that they are very similar, meaning that they form in isolation. The center image, you see the mass of the dust disk masses of our sources in Lupus compared
sorry, we compute the dust masses of our sources in Lupus along with other brown dwarf disks observed with ALMA in low mass star-forming regions, and we see that all the sources are compatible with a formation similar to the stars. Finally, we report the first detection of the base of a bipolar molecular outflow in a very low mass source. You can check the main work in today's archive. Thank you for your time.
Thank you, Alejandro. Next one is Jake Simon. Jake, you ready?
Yeah. Hello, can you hear me?
Yes, all fine. Please go ahead.
Great. Okay, hello everyone. I'm in my talk, I present some work that was actually carried out by my former graduate student about a year ago and just recently published in AppJ. We're interested in forming or looking at how planetesimals form via the streaming instability in turbulent disks. And so the streaming instability is a way to concentrate particles into these sort of streams, and then those streams collapse when they get dense enough under their own gravity, and planetesimals are formed. But a lot of studies, a lot of work has yet to be done on understanding how planetesimals form in more realistic environments. And you heard my postdoc Daniel Carrera talking about how they form in pressure bumps. Well, we're also interested in looking at how they form in turbulent environments, even if that turbulence is weak. The main takeaway of the talk is that for strong, a higher Z value to the gas surface density in order to overcome the barriers associated with planetesimal formation. And so that's the key takeaway. And
Jake, I think we're kind of losing you.
To go to my talk to see.
Sorry, Jake. I think we lost you. Let's do something. Let's move on to the next speaker, and then we'll come back to you, and you can do it again in case the connection is better. Okay. Okay. So last but not least, Susan Terby, are you there?
Hi.
Yes.
Can you hear me?
Yeah. All fine. Go ahead, please.
My name is Susan Terpe, and I'm talking to you from sunny California. Our project is to model protostars to connect cores to disks in order to trace collapse motions and chemical inheritance. And we do this in order to compare with ALMA data. You can watch my talk on how our model, which is called RADCHEM-T, works. It predicts chemical abundance for 292 chemical species simultaneously. One result is shown here in the middle and right figures in the position velocity diagrams for C18O, which trace dynamics. And PV diagrams are useful for showing disk rotation and also collapse motions. You see that there's a good correspondence. We're mostly seeing emission from the infalling envelope clearly shown in the PV diagram as well as the disk. Thanks.
Thank you very much, Susan. Jake, let's try once more.
Okay. Sorry about that. I've been wrestling with my internet company for a while now.
It's fine.
All right, so to take two. My group and I are interested in how planetesimals form via the streaming instability, which you heard a little bit about from Daniel Carrera earlier. And one of the things that my previous grad student, Daniel Gohl, looked at was how planetesimals form in turbulent environments, such as what might be present in disks, even if that turbulence is relatively weak. The main takeaway is shown by that plot there, which is the critical line between collapse above that horizontal dash line and below where there is no collapse into planetesimals. And so above that line, planetesimals, below that line, no planetesimals, as a function of different alpha values. And the main takeaway is that for stronger and stronger turbulence, you actually need a higher concentration of
of pebbles in perhaps, say, a dust trap or a pressure bump in order to get planetesimal formation via the streaming instability. So this is, again, pointing toward the notion that these pressure bumps, like those seen in HL tau, could be a good environment for planetesimal formation and may be, in fact, necessary to form planetesimals, even if the turbulence is relatively weak. And yeah, go ahead and go see my talk and ask me questions on Slack.
That worked.
Excellent. Thank you.
Thank you. Very quickly, I just want to thank everyone for not going over the time limit, and I'll hand it over to Enrique.
Yeah, thank you, everyone. Thank you, all the speakers in these short presentations. Thanks again to all the speakers today, Akimasa and Christophe. They made a huge effort. Thanks to Misato as well for chairing the session, and thanks to all the panelists and the moderators of the discussion. I think it was very interesting. I'll see some clapping. Thank you. So let's meet tomorrow. Tomorrow we're starting back again at 3 UTC, so 15 UTC. And yeah, let's continue the discussions on Slack. The Slack has been great. It's been very lively. So let's meet there and see you tomorrow.